Hey, how's it going?
Good to see you.
Good to see you.
Excited to be here.
Yeah, good to see you. Okay. Hello, everyone. Can you hear me over the mic right now? It's very exciting. It's great to have you all here. Okay. Okay. Hello, everyone. I'd love to get started. We're a little bit behind schedule, but that's okay. So I'm gonna jump through some welcome, introduction, and logistics quickly, so we can stay relatively on schedule. So I apologize if I jump through these a little bit quickly. But I'm Sophia Makarowicz. I'm the chair of the CESM tutorial committee this year. You'll see me all week. Elizabeth Faircloth is probably handling important things outside right now, and you all know her over email, and you'll get to know her this week. Welcome to the Mesa Lab. As you could probably tell, it's a beautiful place to be and to learn and to work, and so you made it. Congrats. Happy to see you all here. I just want to remind you that we have a UCAR code of conduct, and so when we are interacting with each other, when we're asking questions, when we're learning, please be respectful, be collaborative, consider differing opinions, communicate openly, and be mindful of others. That's the expectation for everyone, and so if you feel that anyone might not be abiding by this code of conduct, please speak to Elizabeth or Cecile Hannay, and so you can contact them through these emails here. All of these slides will be uploaded and available to you later. We are your primary contacts throughout the week, and so I'm Sophia, Tutorial Science Chair. Here's my email here if you have questions about the tutorial materials. Elizabeth, of course, you all know her, the tutorial coordinator, and here's her email here. And so our main goals for you throughout the week are that as a result of attending the CESM tutorial, you will gain a foundational scientific understanding of the core CESM components and features, be able to run and modify the model and use the output, have opportunities to network with peers and CESM scientists, attain an understanding of high-performance computing needed for CESM, and perceive the tutorials to be an inclusive learning environment. And so here, the tutorial website with the link here, or just search CESM tutorial 2026 NCAR, has a lot of information, the agenda, the link to the lab tutorials, other logistic information. Of course, this is where you're going to be spending a lot of your time in the lab sessions, are the lab materials. And so here's the link above if you haven't already checked out those materials. We have them all neatly displayed in these GitHub pages. The main tutorial agenda is going to follow kind of lectures all held in the main seminar room. So we'll have component lectures, we'll have specialized lectures throughout the week. And then we have lab activities, which will take place in the library, and we'll show you the library later. Days 1 through 3, we'll have you all complete the same exercises. On day 4, you get to choose sort of plotting and diagnostics of your chosen components you want to focus on. And then day 5, we'll have some challenge exercises that you can choose between. The lunch will take place in the Mesa Lab cafeteria. There's vegetarian and gluten-free options. You're responsible for paying for your own lunch. We ask that you try to stagger lunchtime if possible, just because it's a ton of people going in at the same time. So if you're feeling kind of done with the lab a little bit early at 11:30, you might wander off into the cafeteria, or if it's taking you a little bit longer, totally fine, maybe at 12:30, you go into the cafeteria. And then important on Friday, We have a soup, salad, and pre-ordered bagged lunch. And so you have to complete this order form by 3 p.m. today to get a lunch on Friday. And I think Elizabeth will have that at the registration table. Okay, perfect. And then you hopefully signed up for a meet an expert session. I think we're gonna assign you to one scientist, and I think we'll send those out this afternoon. So you'll have your final assignments for either Tuesday, Wednesday, or Thursday lunch. And then optional is you can sign up for a Mesa Lab exhibit tour at noon. Oh, good reminder for me. Okay, I'll go quickly through here. And so following, you know what? We will go to the next slide here. Okay, and so this is important though, is that we're gonna have a daily check-in each day. At the end of the day, after you're done with all the lectures and the lab exercise, we want to know how relevant was the content of the class to your interests or needs? Was the difficulty level of the class appropriate for your skill level? And do you have any additional comments or suggestions? We really value this survey feedback to improve the tutorial in future years. And so every day we will have a survey for you. But if you complete every single survey, we will enter you into a raffle, and at the end of the week, we will give out some prizes, some highly valuable prizes. So that's the other incentive to do it every day. Also, ask questions freely. This is a learning environment. There are no stupid questions. We all come from different backgrounds, and we're here to learn. So don't leave confused if you feel like your question was unanswered. And you will figure out throughout the week that no one knows everything about CESM, not even the experts. So please, ask questions. You sometimes figure out things you didn't intend to figure out from asking a question. Okay, the project account. Please take note of this, as well as the reservation queue. More information about this is in the tutorial materials, so please check those out under resources. There's a Google group, and hopefully a lot of you joined that already. Feel free to join that, as well as auditors if you haven't. It's been really nice to see people's introductions here. On Thursday, we're gonna have a special CESM cafe where a ton of people in the lab are gonna come to network with you from different specialties. So stay tuned for that. Here is the main floor. In the main seminar room, you're in that green room. And so the important rooms to you are the cafeteria there, which is on the first floor as well. The women's restroom, you can see there, and there should be a men's restroom on the front, or yeah, there we go, men's restroom in the blue. And then on the second floor, you probably saw the stairs on the left before you entered this main seminar room. You can go up the stairs, turn right, and that's how you get to the library where the labs will take place. There are several quiet places. If you need a break, please ask the admin team for the available rooms. And we don't have time for questions, but please feel free to walk up to me and ask any question you want. Again, no stupid questions, and we're really happy to have you here. Next, we are going to have the CESM Chief Scientist, Dave Lawrence, give a talk.
Okay, well, welcome everyone. Really glad to see everyone. It's really fun every year. This week is one of our favorite weeks here in the CSM activity. Before I get started, I really want to thank Sophia and Elizabeth. They put a ton of work into this every year. It's a big activity. We want things to go smoothly. It will not go smoothly. Get 80 people with different backgrounds trying to run a pretty complex model. So please be patient with everyone. I'm waiting for my slides to come up. But you're going to have fun. I think you've probably heard from some of your fellow grad students or something like that this is a pretty fun week, and so I think everyone hopefully is going to come out with the experience like making some new friends and thinking about some new science ideas and really getting excited about using CSM in your daily work. So So I'm going to give an overall intro, pretty high level, to the CSM activity. So I am Dave Lawrence. I'm the chief scientist. So I'm sort of managing the overall project for the lab and for the community. And you probably know this is why you're here, but just a refresher, what is a global Earth system model and why do we use it? So these are, very, very large models of the Earth system where they use, based on physical equations to simulate key fields and processes in the atmosphere, the ocean, land, sea ice, land ice, et cetera. Many of the processes at the resolution we tend to run are at below the grid resolution. And so we need to parameterize those. And so you'll learn about parameterizations all throughout the week, but a big part of building an Earth system model is constructing good parameterizations to use within it. So that's a big part of what we do. And then really they build on our understanding of everything we know about the world, from observations, from really high fidelity models. And I kind of think of Earth system models as being, without being too grandiose, sitting at the top of the Earth system science pyramid, where we have many researchers around the world collecting data, synthesizing data, understanding data, and that then builds on process-oriented models, and then that we learn from that and build into a global Earth system model, which then helps us to understand the world and all the ways it interacts. And so this is what a structure of CSM, or really any Earth system model, looks like. It's usually built around a centralized coupler, we call it, and then there's different component models. So an atmosphere, a land, a sea ice, a land ice, ocean, river, and each one of those models can have different subcomponents like chemistry or biogeochemistry. And they pass information back and forth between each other, and as the model advances, time step to time step. And then there's typically forcings that come in there too. So that could be greenhouse gases, it could be anthropogenic aerosol emissions, it could be volcanic eruptions, it could be solar variability, it could be land use change, it could be any other thing we need to sort of prescribe to get in the system. And they're really used for many different things. And over the course of your research careers, if you get involved in using Earth system models, you're really only limited by your creativity in terms of what they can be used for. So, scientific and mechanistic understanding of past observed events and changes, obviously studying recent, past, present, and future projections, climate change and their impacts, one of the original reasons why these models were developed, in addition to understanding weather. Understanding climate variability are really important, subseasonal to multi-decadal predictions. So we use CSM to do predictions on all different timescales to help us, help forecasters build better forecasting systems, and also providing actionable, societally relevant information. So decision making in a changing world is really a key reason for system modeling. And as you're all, I'm sure, fully aware, is that the output from these Earth system models forms a basis for the IPCC reports. As our understanding of climate change, huge fraction of that, or a big fraction of that, is coming from Earth system models, and that's, Earth system models were part of the reason why we can say for a long time now that the Earth is warming unequivocally and climate is changing, and then really understanding the implications of that across all sectors. Okay, so this is CSM2. So I'm going to talk about CSM2 and CSM3, and you'll be using CSM3 during your workshop here. The model is not yet released, and I'll get into that a bit more, but you'll be working with our most cutting edge model this week. So CSM2 is composed of these different atmosphere components. It was the configuration that we used for simulations that we used for the Coupled Model Under Comparison Project 6, which is the big international activity that we used to provide simulations that are then drawn these simulations for IPCC reports and many other things. And it's also the configuration used to generate our large ensemble, our most recent large ensemble, the CSM2 large ensemble. And you'll be hearing about large ensembles this week as well. And so it's made up of our component models, some of them coming from developed at NCAR, some coming from external, like the ocean model and the sea ice model are both developed externally. The WaveWatch model as well. So it's a big mixture of different major component models. There's many Earth systems all around the world. There's roughly 10 big ones. There's 40 or more that participate in the CMIP activity, but 10 or so really fundamental core models that provide most of the innovation. And CSM is one of those leading models. And I think it's fair to say that it's the most widely used model, partly because we do things like this and provide tutorials to the community, partly because it's completely open. It represents over 30 years of development. So this is a tool that's been built up by scientists and hopefully you as well in the future over many, many years. It is a true community model. It is the only real Earth system model that has full level of support in terms of developers. So we support developers who want to help them make the model better, and we also support users. And so we have a big user forum used by researchers all around the world to help each other use the model effectively. And it's got strong community participation, more than 2,000 researchers involved in the CSM activity overall, and it's really widely used. If you go to AGU, or when you go to AGU, you're probably going to be seeing talks with CSM, more than 400 talks a year, 400 to 500 talks at least, probably an undercount of talks at AGU. And it's really big. It's like Sophia said, nobody can understand the full scope of CSM, 4.5 million lines of code of Fortran, and we can talk about Fortran versus other languages if you want to. Big topic around here these days, but nonetheless, it is very big. There are over 1,000 geophysical variables that it spits out. So pretty much anything you can think of that you want to think about looking at in terms of a variable, CSM is probably producing it. And I like to think of it as a virtual laboratory. So, you know, we run here at NCAR these big key simulations with climate change projections, but really you'll use it as a laboratory where you're trying to make modifications to it to help you, disentangle how the Earth system is interacting with itself. So it can be used to study Earth system variability and change, air quality, biogeochemical cycles, solar functioning, process understanding, land, ocean, and other interactions, ice sheet climate interactions, hydrology, ecology, Earth system predictability, weather from local to global scales, et cetera, et cetera. And the way we do this is we've developed it very intentionally to be very flexible. And so we support a very broad range of climate and even beyond climate, weather to climate, continuing research questions through a single model code base. And so if this is what the CSM looks like in all the bells and whistles, everything turned on, it also has the capability with just a simple one-line change in the code to switch from going that fully coupled to another configuration where you're running with a data atmosphere and an ocean and a sea ice. So you're maybe just interested in the ocean sea ice problem and you want to forest with observed atmosphere. And so it's very easy to switch back and forth between the two so you can understand the role of coupling versus uncoupled. And with the state atmosphere, it's providing this sort of the weather information, temperature, precipitation, and all the fields needed to drive the surface model. And then maybe you're interested in biogeochemistry, so you could turn on the biogeochemistry configuration and what we call Marble. Or maybe you're interested in land processes, and so you run the same thing except for running with the data atmosphere, but forcing the land and the river model in uncoupled fashion. In this case, then you might have, and within each component model, there's many different options as well. So you can probe down and say, okay, I want to put in a different land use change data set, or I want to turn on biogeochemistry, or turn on the active crop model, or prescribed vegetation. So within each one of these component models, there are many, many options within it. So as you start, you see fairly quickly that it becomes a combinatorial opportunity, and that's where a lot of your life is going to be, is trying to figure out how to make best use of all those options to understand the topic that you're most interested in. And here's just another example of the chemistry. You can turn on atmospheric chemistry, and we have four, actually even more, but four normal atmospheric chemistry modes with varying levels of complexity in terms of the number of species that are represented. And so again, if you're interested in chemistry, you might go with one of these configurations with more complex chemistry, which can be computationally costly. Or if you're not as interested in chemistry, you can go with what we call the specified oxidants version, with a more simplified version of chemistry. That's what I like to say. Earth system modeling is hard, and so you're gonna learn a lot this week. It's going to be a lot to take in, but really you can think of it as Earth system models and data as a tool in your research toolbox. So this week you're going to learn about a bunch of things: the component models within CSM and the science behind them. It's really important that you understand, at least to some degree, the science throughout the code, how to set up, run, and make simple modifications to CSM. And also some ways that CSM is being used to address the critical science questions and a broad range of science questions. But really, this is just going to be the beginning. Learning how to usefully apply ESMs and ESM data to answer research questions never ends. And our advice, my advice, our advice is to be creative and acknowledge that we miss steps and really to have fun. My postdoc advisor, many moons ago now, when I was sort of struggling with my first step into Earth system modeling and producing some figures and some results, but nothing that was really very innovative. She said, "Don't stress it. It takes 5 years to become a good Earth system modeler before you start producing really impactful research." Now, some of you here are going to be way smarter than I am. You're going to do it really fast, but also just to say, don't get frustrated if it takes you a bit of time before you come up with something that's really going to like move the needle in terms of scientific understanding. Okay, so one of the things that I like to way to introduce, how to think about how to use an Earth system model is thinking ahead of time as you're starting a research activity. Like, how do you want to invest your? Often it's computational resources as a limiting factor. It could be time resources. It could be understanding resources. You have to think ahead of time, like, how do I want to approach this problem? And so we typically, as we start any research activity here at NCAR, we think along these three axes. So we have a certain amount of compute or data storage availability, and we have to decide where do we want to spend our computational effort, either in model complexity. So if you go with the most complex model, that's going to be more computationally costly. You might have a question about how long, if you're doing short-term forecasts versus long century scale simulations, that's going to have an impact on compute. And then also resolution. The higher resolution, usually you get higher fidelity simulations, but it costs a lot more. It goes up very rapidly in terms of cost. And so, the first one is complexity. So the growth of climate modeling has enabled these models to become intensely complex pieces of code. In the early days, we just had relatively simple configurations with simple oceans and simple atmosphere and land. Got decoupled. We added sea ice. We've added aerosols. We've added interactive vegetation, biogeochemical cycles, carbon cycle, ice sheets, marine ecosystems, upper atmosphere, atmospheric chemistry. We keep adding as we go forward. So you have, as I pointed out, options to make decisions about what level of complexity you need for your problem. This is the one for ensembles, so you'll hear about large ensembles quite a bit this week, I expect. And that really helps us understand the role of internal variability versus the forced variability from climate change, or it could be something else from CO2. And so this is a nice example. This shows you that if we run CSM 100 times out into the future, you can see there can be a lot of variability in the climate change response. And this is just showing out of those 100 members, this is the wettest member and this is the driest member. And so you see a big difference in the projection, and this is the average over all of them. And so if you want to understand climate change, you really need to understand the role of that sort of internal variability relative to the forced variability. And then resolution. CSM is built so that we can modify resolutions either globally or regionally if we need to. And resolution can make a big impact on your science, but of course, as you go to high resolution, it becomes much more costly. And so we've done a lot of experiments here, and this is a slide that sort of summarizes what we've done. So this is some of the data that we provide to the community for many things, including AI training, which I'm not really discussing here, but the slide, it was important when we saved the slide. So different simulations, which are not going to mean too much for you. This is our high resolution configuration. This is our kilometer scale. These are our CMA 5 and CMA 6 contributions, large ensembles, last millennium ensemble, perturbed parameter ensembles, and decadal forecasts. And the main point of this slide is just to say that we have a lot of simulations available for researchers to go and download and use, or get onto Derecho and use. And so for many of you, that'll be your first stop, is to, in Earth system modeling, is to find the data set that is most relevant to the work you want to do, and then use it. Okay, so CSM2 is a model we've been using for the last 7 or 8 years. And so you will be hearing about it a lot during the week. We're trying to transition our tutorial to CSM3, which we're releasing later this year, but there'll be some mixture this year for sure. But we are moving to CSM3, and it's an update. We've changed our background graphic, but also changed all the component models. So all the component models have been major upgrades to them. We have some new major capabilities, emissions driven, which we actually had before, but it's going to be more focus, interactive Greenland ice sheet, new ocean and wave models, new atmospheric dicore, and many MPAS, and an option to run the MPAS dynamical core, and new physics across all the component models. And you can see the full list of changes at our website, and the intention is to release this model by the end of the year for everybody to use. But you will be using this model this week during the tutorial. I'm not going to go through the updates except to say that there's just updates throughout the code. There's at least 50 new capabilities or features or new physics within CSM3. Okay, so for the second half of my talk, I want to sort of talk about what's coming next, because we are always thinking about what the next things are, and you're here probably because you're interested in CSM and maybe going to get involved in building the next generation CSM, and it's a really interesting time to be involved in Earth system modeling. The world is changing in a lot of different ways, and the world of Earth system modeling is also changing, and so these are a set of slides I put together to try to encapsulate that. And so fundamentally, I think this is not news to anybody, but fundamentally that, the overarching question about whether climate change is happening or not is not, it's not the question we're trying to address anymore. That was the driving force for a long time. But now really we need to provide, actionable climate change or other information on climate risk, the consequences of intervention and mitigation for people to make decisions in this sort of changing world. And that's really the critical, one of the most critical needs for a system model. So how are we going to address, the changing extremes? How are people going to adjust to changing extremes? And I think I like to put it this way: is in a more, sort of more iconic way, is to say, where and when will people and ecosystems experience more extreme events? Will we have enough water? Fundamental questions. Or will we have too much water? Will there be enough water to irrigate our crops? And along those lines, will we be able to grow or harvest enough food? And can we produce it sustainably? Critical question. And I think what's interesting is that these models we have produced are pretty good at a lot of things. And there was a nice workshop about 2 years ago now that we held here at NCAR that asked the question that a lot of the trends that we're seeing in Earth system quantities are long enough now that we can start asking the question: are our models able to capture these realistically? I mean, we have in many cases 60, 70, 80 years of data that are useful now. And so there's a nice workshop where we asked them a question about confronting Earth system models trends with observations. And the summary of this paper, led by Ella Simpson, I think she'll be giving a lecture this week. She's definitely here this week if you want to meet with her. Is that we do some things really well. Some things you can't really trust the observations, is sort of the conclusion from this. And some things we definitely have opportunities to improve. So we can make these models better and more actionable. And there's still many opportunities to improve these models. So I really recommend this as a nice paper to kind of think about the kinds of things we could be doing to make models better. But nonetheless, it provides impetus for us here at NCAR to continue to develop the model. And so, yeah, what are the potential and the consequences of climate intervention is another key topic. We don't want to have to do this, obviously. Things like solar radiation management, SAI, carbon dioxide removal, we do want to do. But we need to understand what the consequences are, and that's a big research program here at NCAR around the world. And then the other really fundamental question is, where are we going to put the carbon, and will it stay there? And then lastly, in terms of the key priorities, understanding the potential and probability of tipping points. That's a really hard field, and that's what our system models should be good at. And there could be a tipping point that's just around the corner, and if we're not ready for it, we're going to get surprised. So we obviously need to be continually focusing on the potential for tipping points. And so, if you say that's the thing we're trying to do, actionable information, how are we getting there? There's many different pathways to try to get to more actionable information. One is trying to move to a higher resolution. And our standard resolution is about 1 degree right now. The CSM3 we're developing will be 1 degree, but we do have configurations at higher resolution where finding those simulations are really useful. And also ultra high resolution, like global kilometer scale simulations we can now do, and you can learn things about the world at those kilometer scale resolutions, even if you can only run for short periods of time. Obviously, machine learning, AI, hybrid modeling, emulators is a really important space. There's also just this need or desire to have sort of a seamless Earth system prediction and predictability capability across timescales and space scales if you can, from subseasonal to seasonal, S2S, seasonal to decadal, S2D, or even 30-year projections. And so if we can be using roughly the similar modeling system across these different timescales, we feel like we can learn things and feedback on each other. Then there's the changing competing architectures in languages and our need to do code modernization. Obviously, GPUs are all the rage these days, and a lot of the supercomputing centers around the world are transitioning to GPUs, and is our code ready to run on GPUs? And the other thing is Fortran is a language that's fairly old now, and there's new languages. Can we or should we be transitioning to different languages? And then also, for us, it's really important to maintain or improve accessibility of Earth system models and Earth system model output around the world, especially to the global south. The people being most impacted by climate change are often in less rich places, often referred to as the global south, and they're usually not involved in the climate science activities. That seems wrong. It is not just seems wrong, it is wrong. We need to get those people involved, and so that's an important priority for CSM. So these drivers present many opportunities and challenges for us. The first is, this, like I said, high resolution. So we have a high resolution configuration, CSM 1.3, which we've run a relatively significant ensemble with, and you'll be hearing about it this week. It's a really nice and novel set of simulations that we're learning a ton of new stuff from. And so we're excited about that. But we didn't produce one for CSM2 because we sort of ran out of time and energy, but we are planning one for CSM3, a high resolution version, which will be quite expensive. And then there's the earthworks and storm speed activities, which support the kilometer scale configuration work that we have. And so those activities are moving along. We now have quite a few kilometer scale uncoupled simulations, and we're moving towards coupled simulations with the ocean. And then we have the capability within CSM to run regional refine. So you can telescope in your region of interest to get high resolution for a significantly cheaper cost. It's still very expensive, but it's much cheaper than if you're doing global kilometer scale resolution. In terms of AI ML, one of our big activities is pushing towards a hybrid configuration, so a combined physics and machine learning version of CSM, which we're going to call CSM3 MLE for machine learning enhanced. And so in this situation, we're using AI, new ML algorithms, to build new ML-based parameterizations based on information we can learn from high-fidelity models or detailed observations or satellite observations. So we can replace our existing parameterizations with these new parameterizations where the machine learning is essentially learning more details about the processes than sort of we were able to do as we developed these parameterizations previously. And we're also using it to develop parameter calibration methods for both the component models and hopefully moving towards the coupled model as well. So we get closer to observations by doing model calibration, which was traditionally been sort of too computationally expensive to do at the global scale. And then produce the next generation CSM, and hopefully the hypothesis will have more accurate model and therefore more accurate or reliable projections. So these are two big activities supported by these two big projects, LEAP and M-squared lines. Another priority for us is moving towards more research at shorter timescales, so this Earth system predictability across timescales activity, really trying to have this nice merger between impacts and risk and understanding how predictions can be used, and also understanding how we can make better predictions. And NCAR is not an operational center, so we really focus our activity on research. So we try to build a system where we can play with the predictions and sort of modify them and see where we can get the best gains, and then that information then can feed into the weather centers as they update their systems. And really focused on a pretty wide range of timescales and processes. Okay, so that's some of the things going on with CSM. There's many others, and I'm happy to answer questions when we get to the question and answer session, and you'll be hearing about some of these activities throughout the rest of the week. But if you want to get involved, so the best way is getting involved through the working group. So we have a working group structure with CSM that we've had since its inception. It's really effective, a way to engage, provide this platform for engaged community, that's you, model development and application. So we have 12 different working groups. The ones in darker blue are model development working groups. So these working groups have part of their focus is on the development of the component model they're responsible for, although there's a lot of science activities that go on with each of those working groups as well. And then the ones that are a bit lighter colors are more focused on applications, so biogeochemistry, climate variability and change, Earth system prediction, and paleoclimate working groups. And these working groups are open to anybody. All you have to do is sign up to the mailing list. We have meetings throughout the year. You can drop in and join model development meetings if you want to. There's many opportunities to get engaged. And this is a relatively new slide I created, which I try to emphasize the point that NSF and NCAR provides the backbone for the CSM ecosystem, but the community really makes it thrive. And the community is you. And so we provide this backbone and things like tutorials and computing platform and support, but then it's the people like yourselves who come and use the model and assess the model and probe the model and then feedback that information to us that makes it a thriving ecosystem. And so none of this stuff works. You can't do the model development if you don't have an understanding of how the model is doing. And you need to produce big simulations to be able to help the community understand what the model is doing. And also to do applied research, and then you need the basic scientific and technical support to allow the community to thrive. And then underlying all that is this critical software infrastructure that allows everybody to seamlessly use CSM. So some learning engagement opportunities. There's a tutorial, so you're here, so you've learned about that. And the tutorial is all online, so you're going to be able to tell all your fellow students as you go back about the tutorial and point them to the materials. They can learn online if they want to. It's all run, as you'll see, through Jupyter Notebooks. There's many mentoring opportunities, so you'll have an opportunity this week to meet a few NCAR staff if you want to. And we really enjoy hosting students for longer visits. So if any of you have faculty who are amenable to letting you take off for the summer or whatever it is, we host. You'll see a lot of students and postdocs here visiting as you move around this week. And so we really enjoy working with students and postdocs and even faculty. And we do have some programs to support that as well. And then there's the annual workshops that we have. So we just finished our annual workshop in mid-June, and then we have winter working group meetings in usually around February, March timeframe. And so if you're on the mailing list, you'll hear about that. And again, that's a great opportunity to come and spend a longer period of time with experts, using the model, and you can get to present your results and get feedback on it. So we had our 31st annual workshop a couple weeks ago. Our 32nd annual workshop is June 14th to 16th in 2027. So you can put that on your calendars. And these are pretty big workshops. We had 230, 240 people in person this year, 210 plus presentations from 150 unique institutions. And so that's quite important to us to kind of track this and understand how we are sort of impacting the research community. And so we hope that some of you will make it to our next CSM workshop or one coming in the future. And I think we are going to have a program to try to track students as well. Elizabeth is working on that. I can't see if Elizabeth is here anymore, but to track students and see how the CSM tutorial is impacting your careers, because we've got a lot of colloquial understanding that it does have a significant impact. So that's all I have. Thanks, and we really want to welcome you to the CSM community. Hope you have a great week. Enjoy yourselves and learn a lot. And yeah, I'll take some questions.
Any questions? I think I can hand out this mic. Okay. Oh, above? Okay. Oh, great. We have a little over 10 minutes for questions.
Someone back there was first.
Yeah, go ahead.
Oh, hi. You mentioned that paper from Ella. I remember that paper is talking about the vapor pressure deficit. The observation is different from the CESM. So I'm working on the hydroclimate change over Southwest North America, so that's the same region. I'm wondering if there are other components or from the CESM that's the observations and the simulations are very different.
Well, that paper outlines a few things. There's some circulation issues that the model has in terms of predicting the historical changes. I can't remember the whole list. There's a nice table in there which shows the ones where the model captures things well and models don't. So yeah, I don't have like an immediate list off the top of my head, but yeah, that's part of the reason to be here this week is you'll learn about some of these where there's discrepancies. We've had a problem until recently with the ocean SST patterns didn't match up with observations, and that's been a big challenge for the system modeling community in general. We have an interesting result that our high resolution configuration, CSM1 high resolution, can get the SST pattern. It looks pretty similar to what observations is, and so we're trying to understand, the source of that. So that's interesting. And one of our ensemble members, or a couple of our ensemble members. So that's another example. In terms of that question you're asking about the water vapor trend, we are still working on it actively. So I'm on a project with Isla, and we are still trying to understand it. And I would still say that we are perplexed by it. We can't really figure it out. And it is common to all risk system models. So a pretty interesting and challenging problem. So, yeah.
So I also have something about the land process. If you have time later, we can talk more.
Yeah, absolutely. Yeah, I'll be here, and I'm going to do the media scientist, I think.
Yeah, Dave is an expert
Okay.
this week.
Yep.
Good morning. I was wondering if you wanted, since we had the time, if you wanted to comment a bit more on some of the more specifics about the discussion between upgrading from Fortran if it's necessary, what role machine learning has and all of that, just kind of get us up to speed on that debate a little bit.
Yep. Yeah, it's a big conversation here at NCAR. We talked a lot about it at the CSM workshop with some of the leadership team. You have to think about what the motivation is, first of all. And one of the motivations is to get code that will run on GPUs, which might be faster. It's actually, a lot of people say it's going to be faster without sort of all the qualifiers. It really depends on the resolution. Our sort of current thinking is that at our low resolution, we won't get anything from GPUs, but the high resolution we might. So that's the motivation is to get it. So you can do that within the Fortran world. There's a way to do that. There's a question of whether it's the right thing to do in the long term. And the other reason to do code, to transition to a different code is for accessibility. So we know that most graduate students or most people around the world are in some sort of Python-based language, and that's where people are learning. And so that's important as well. That's an important consideration. And so sort of those are the two primary motivations. And then just some of our code is old now, and especially. Some of the older code is kind of spaghetti code that's kind of difficult. It's not as modular as it should be. And so as you're going to do any sort of code modernization, you want to clean the code up to make a better, code that can maintain for the next decade, And so we're thinking about all these things. What's going on with AI and things like Claude do make things potentially better. We have some pilot programs where people are translating code, sometimes successfully, sometimes not successfully. You'll hear some stories that it's super easy, but most people are being realistic to say it's got its own challenges as well. But we are working on it and trying to come up with a path forward. And I'll just say it's pretty complicated. Such a big code base, so many users, and changing computing architectures. So I'll just say what we are trying to do is do sober, realistic analysis of it and try to move forward in a coordinated fashion. And that's going to be a challenge. But yeah, we're on it, sort of. There's one here.
I noticed in the figures showing the different parts of the model that biogeochemistry was linked with like the ocean component. Is it particularly linked with that, or does it also I'm not sure the terminology, but integrate with the land portion of the model as well?
Yeah, the reason we have it drawn like that is just because the Marble code it's its own package, and so it's coupled to the ocean code, and so you can kind of pull it out, and Marble is used in other models. On the land side, we also have biogeochemistry in the land, and it's more deeply integrated into the community land model code. And so we have a full biogeochemical model within CLM as well. But it's not, you couldn't just pull it out and add it to another model easily. So, yeah. But yeah, the model does full global biogeochemistry, which then means we can run in what we call emissions-driven mode, where you just prescribe the CO2 emissions from industrial use and then let the Earth system respond to that and to predict the CO2 in the atmosphere. And we can do that, and we can essentially replicate the historical observed trend in CO2 And then that allows you to make projections of CO2 with all the your system processes interacting.
I have a quick question, maybe not purely about science. So for the future stage or future version of CSM, would be more cooperation between like NCAR and probably other companies, etc. Because some of like AI and machine learning related corporations, they begin already to touch the regime of earth sciences. And I'm also interested in like for the next version, how heavy will CSM rely on machine learning stuff, or like it will be really cautious or etc. Thank you.
Yeah. So in terms of interaction with companies, I'm not sure exactly what your question is. I mean, there is obviously there's a lot of work by the tech world to produce emulators or foundation models, often for weather, really good for weather, right? I'm sure you're aware of that. With mixed or more complicated results for climate timescales. And so we are certainly in conversation and sort of in the broader collaborative sense with all these groups who are trying to do this. And so we are regularly going to the same meetings and discussing processes and discussing how to analyze those especially the climate models. There's an activity called the climate bench, so they're trying to put together a set of diagnostics that would be able to test a climate emulator, climate foundation model. In terms of, and so we have some collaboration with NVIDIA, Google, et cetera, mostly unfunded, but we're talking with them. One of the activities I didn't mention here, I sort of meant to, but forgot to add to the slide, is that we are working towards, we have the ability to emulate parts of CSM. So there's an emulator of the atmosphere model called Camulator. It's built on a thing called Credit. I think you are going to hear about Credit this week. It's our package that we use to make it easy for people like yourselves to build emulators. And in the longer term, maybe the next couple of years, we're hoping to build what I'm calling a flexibly coupled CSM emulator, AI CSM, where you can emulate any components of CSM or couple them together to build a model that's very fast. So it's learning from CSM capabilities, but it could be run, you could run a huge number of ensembles, or you could turn certain components on to be a physically based component and then couple to an emulator. And so we're not really advertising it because it's not a real capability yet, but our goal is to have that sometime in the next few years. And in terms of CSM, we have this hybrid modeling activity which is moving along in parallel to the core CSM, and we hope to have a version either uncoupled, probably starting with like atmosphere only, atmosphere land simulations fairly soon, and then a coupled configuration a year-ish or more out, which is our main AI focus besides this flexibly coupled emulator. Yeah, we got one back there and then here.
My question is about the accessibility. Well, I spent like 3 months compiling the CSM, and it was very irritating with all the packages and all this stuff. And my question is about if there are any efforts in making like a cheaper version of CSM that is already precompiled or something like that. Because I think it would be like a good way to make this model more accessible.
Yeah, we always have discussions about cheaper configurations, and with CSM2 we had a not well supported 2-degree version. We haven't fully decided whether we're going to produce a cheaper, lower resolution version for CSM3. We know the research community would like to have that, but it takes a decent amount of effort, and we have to just decide how to spend our essentially staff resources to do it. So we recognize that that'd be useful. In terms of like precompiled, we do have the ability to run in the cloud, and you can with a I'm blanking on the term this morning. What's the term of the package?
Container.
What's a container? Thank you. With a containerized version of CSM that you could have access to, and so there are ways to do that, but it depends on how much to compile is the problem, or the cheaper configuration. I'm guessing the cheaper is the thing that you really want, and so to be honest now, we don't know what we're going to do on that.
Yeah, thank you, Dr. Morris. I think I have a broader question. I usually saw when in the end of papers, people usually say that our findings may be helpful to improve the predictability of climate models. So I'm wondering how important or confident or like groundbreaking the results should be to make it improve the predictability. I mean, how would you like maybe update the frameworks or equations based on the most recent findings in papers?
Yeah, that's a really great question. I like that question because it gives me a chance to encourage you to. So these models are really big, complicated. It is often very difficult to establish whether or not you're making the model better or not, because there's a lot of internal variability. There's many processes interacting. There's probably problems elsewhere in the model that are sort of masking, or even if you change your problem, it might actually make it worse because there's some sort of other competing bias somewhere else. And so, at least my philosophy, and it kind of varies across different people, is that what we're aiming for is to get the best physics we can into the model, and then we try to make a simulation that looks good. And so, in terms of what do we accept as a new development, usually to me the first fundamental is it better physics? Can you argue in some way that the physics is better than it was before? And then if it is, I think we try to bring that into the system. Now it can take quite a long time between a paper. Actually, if you just write a paper and submit it to a journal and then get it published, and you don't ever talk to us, that's probably not going to ever make it because there's just too much, right? There's, like you said, every third paper says they did something to make our system models better. So if you really want to get involved, it's better to come, have a visit, get involved, spend some time, build it, create a PR with help with our software engineers, and bring it in. So it's a kind of a long process. It can take, multiple years even sometimes if it's a big one. But that's the way it has to work. So and I see Sophia trying to run me up, but I really encourage you to do that though, because I get really frustrated when I do see these papers about somebody did something pretty cool, but they never talked to us once. And by the time we see it, the model's moved on, right? And so it's too late for us to even think about taking it in. And so really interact with us as much as possible. We'd rather get too many ideas than have a good idea go past us, at least my perspective. Some of the people who are overburdened might not feel the same way, but yeah. So thanks. Looks like we're on.
Oh, okay.
Are you able to stay for a minute during the break? Okay. Just in the interest of time, now we have a break. Dave can stay a few minutes for the break, and so feel free to ask questions over the break. But yeah, we'll break for 15 minutes for coffee and come back at 9:30. Thank you, Dave.
Yep.
Hello. Welcome back. We're going to start with our second lecture, long lecture here. Next, speaking, we're going to have Peter Luritzen, senior scientist in the atmosphere section, talk about atmospheric modeling and focus on dynamics.
Good morning. Yeah. If you are an atmospheric modeler, this is the first of two very important lectures. This is the atmospheric component. We sit on top of the land, we sit on top of the ocean, we sit on top of whatever cryospheric components are active in the system. How many of you in here identify as atmospheric modelers to get an idea? Right, so that's like 40% of the room-ish already. So I've tried to make a lecture that speaks to all of you. So please let me know afterwards if there are parts of it that are totally out there, or if I'm speaking down to you, and I don't want to speak down to you. You're all very smart people in here. So just want to make it very accessible for everybody, but not dumb it down either. That's not useful. So we're in the business here of global modeling. So here's a satellite image of Earth. We cannot solve the equations of motion for the atmosphere on a piece of paper unless we vastly simplify it. So if we linearize it, we can solve it in some situations, but the full system we cannot solve. So we need to discretize the system so we can implement solvers on computers. So it doesn't matter if you use, what should I call them, traditional discretization methods, or if you're using AI models, you need to discretize the system. So here is a regular latitude-longitude grid overlaid this image here. As soon as I define a grid, I define a size. So inside each of these grid points here, we have all our prognostic variables. So there'll be your wind components, your pressure fields, temperature. It will be all your chemical species and so on. So we have those defined as grid cell averages inside of these grid cells. And what I'm going to focus on here is the dynamical part. So that's loosely referring to how we solve the equations of motions on resolve scales. So in modeling jargon, this is called the dynamical core, die-core dynamics. But one thing I do want to highlight here is that the smallest scales on this grid here, we're not representing very well in our dynamical core. You can view, or you can study this in several ways. Some of you might have taken classes where you linearize the system, do a von Neumann analysis, and they will tell you how much different wavelets get damped and dispersed. So they will give you an idea of what the errors are. Another way of looking at this is doing a power spectrum that I've shown here. So you have short wavelengths on the right, long wavelengths on the left here, and then the energy density here. And if you go out and measure, for example, the winds at 200 hectopascal, you will see that in the large scale of the atmosphere decays in like a -3 scale, and then you go into the -5/3 as you get into the mesoscale. But what you can do is you can compare what observations show you and then compare what your model shows you. Don't look at the right plot, just look at the middle plot here. This will show you CAM run at different resolutions here, all the way from 1.5 degree, that's the blue line there, all the way up to 1/4 degree. And as you see, as we increase resolution, the curves move to the right. I mean, we have more energy at smaller scales, but you also see they all fall off. Some people like to define that as the effective resolution of the model. Like, when do we don't have the same amount of energy at the smaller scales as we do in nature, then we know now we're not representing things as accurate as we could. That cutoff is typically 6 delta x-ish, 4 to 6 with higher order methods. So that means if you have a 100-kilometer model, in terms of this approach, you can trust the 400-kilometer wave and longer. So just a heads up that be careful with the smaller scales if you're looking at output from any model. What happened here? Okay. Here's just another illustration of numerical errors. Absolute simplest problem you can deal with is a 1D advection problem. You have wind blowing from this side to that side. The square wave here, that's the analytical solution. It will just be transported indefinitely, not changing shape in the direction of the wind in 1D. And then I've shown the absolute simplest numerical method, forward Euler solving this equation. Let's see if this works. It does. You can see here it will reduce the amplitude of the wave. It will also not quite propagate at the right speed. So those are the kind of numerical errors that exist in modeling systems. We use higher order methods, so we are not as bad as that one, so I'm just exaggerating here. Okay, see if I can get back in. Go. Alrighty. So as I mentioned, I'm going to focus on the resolve scale. There's also an unresolved scale, so what's going on subgrid scale. That's a very vast topic. Basically, you're giving a parameterization. What are the winds, what is the temperature, what is the pressure, figure out what's going on subgrid scale. So there's a whole lecture on this this afternoon or later in the week. I actually don't remember. So in terms of the model code, even though nature doesn't have this separation, we do separate the two here. So if you look at the GitHub repo here for CAM, there will be a dynamics repository where all our die-core solvers are living. Then there'll be a physics repository, and we actually have several. This is the old physics. We're right now porting our physics to a different framework, so some of the packages will live in this atmos-phys directory. But nevertheless, they're separated. So loosely speaking, the dynamical core here is solving the governing fluid equations or thermodynamic equations on resolve scales, while the parameterizations take care of the rest, loosely speaking. Alrighty, so let's get an idea of the system we are trying to model here. And I've here shown a representation of important atmospheric phenomena in a space-time diagram. So on the x-axis, you have space, all the way down from the millimeter scale all the way to the planetary scale, so thousands of kilometers. And then on the y-axis, you have the time scale of these kind of phenomena. So if we start at the upper right here and just walk down that dotted line, on the order of tens of thousands of kilometers on the seasonal scale, we have the large-scale circulations, Hadley cells. Then we go down to undulations in the jet stream, large-scale pressure patterns. They evolve, in the matter of many weeks. Then we have individual cyclones and anticyclones. Then we can go down to transition zones between warm and cold air, so in other words, fronts. And then the last one here, we have convection, and that's a very, very large subject because convection can be organized on very, very large scales, but it can also just refer to small-scale turbulence in the boundary layer creating clouds. So they can be all the way from thousands of kilometers down to the meter scale here. So very, very large subject to parameterize. So all of these phenomena here along that dashed line here are important for our modeling. The bad news for modeling is that all of these are in a continuum on this line. They're not like separated in scale. So that makes modeling of all this quite challenging. John Fubon, who made this plot here, he also added these dotted lines with gravity waves and internal acoustic waves. The reason I've added those is that they are important for the stability of a numerical solver. So the fastest wave in your system, if you're using explicit solvers, will determine your maximum time step. Otherwise, your model blows up. So we have gravity waves that are pretty fast waves in the atmosphere. They can have many sources. Those are considered important for modeling, but there's also acoustic waves in the system that are energetically very, very weak and not considered important. So if those waves are perturbed or not represented at all, that's not considered a problem at all. So the red line here approximately shows where we're at with climate models nowadays. They're being run at 1-ish kilometers resolution. The time step in the physics is about 30 minutes. So you can see there's a lot of stuff that we do capture, but there's also a lot of stuff that we don't explicitly capture here. We also run CAM down at the kilometer scale right now. I haven't added the bucks from that, but when you start running at the kilometer scale, well, then you actually do start to resolve some of this convection explicitly, and you also represent gravity waves quite well. So as you increase the resolution of the model, you may be able to get rid of some parameterizations. And at the very least, you need to tune your model for new resolutions. Just to give you an example here of cutting-edge science being done with CAM. On the left-hand side is a run at 3 kilometers done with the MPAS DICOR, but with CAM physics. The left-hand side is without deep convection scheme. The right-hand side has the deep convection scheme. And for those of you who are familiar with this, will immediately recognize that on the left-hand side, we have a lot of popcorn convection, and a lot of modeling centers are struggling with this. So most centers running at 3 kilometers do have some kind of parameterized deep convection scheme turned on. For those of you who are familiar, it's the Club MF version that's on the right here, where we get much more realistic convection in CAM when running at those scales. Alrighty. So I'd like to walk you through very fast some of the deliberations you have to go through when you want to design an atmospheric model. So first of all, what do you want to do? Do you want to do numerical weather prediction? Do you want to do climate simulation? Do you want to do paleoclimate simulation? Like basically, what is your time scale? How long are you going to run the model for, and at what resolution? And then what processes of interest to you? Planetary wave, extratropical storms, squall lines, tropical cyclones, supercells. If you're a chemist, you want to add a bunch of chemistry to the system. Maybe you're interested in stratospheric dynamics, then you need a model top higher up to make sure you can resolve that. Maybe you're interested in space weather, so you need a model top at 600 kilometers. All of this has consequences for what equation set you are solving. If you're going down to very high resolutions, you need a non-hydrostatic dynamical core. If you're going into geospace, you need a deep atmospheric discretization. And then also you have choices about what are your prognostic variables. Just to give you an example here, these are common assumptions in global models that are run at about 100 kilometer resolution. And within the last 20 years or so, the dynamical core community has slowly, in the context of global modeling, got rid of these assumptions one by one. The model you're going to be running here has all these assumptions in it. So first of all, we have this spherical geoid assumption. So we assume Earth is just round. Gravity only acts in the radial direction. Secondly, we have the quasi-hydrostatic assumptions. Maybe basically it's a hydrostatic model. We do not have a prognostic vertical velocity. It's diagnosed. If you ask when that breaks down, you'll get different answers. I'll just give you a number, 10 kilometers, approximately where it breaks down. But, you know, some of the best modeling systems on Earth, like the IFS system, ESMWF, are running way beyond that limit. Shallow atmosphere assumption is basically assuming that the layers that we're discretizing are very thin layers. So we do not take into account that as you go out from the center of the Earth, the grid cells actually expand like this, and you actually have a full 3D Coriolis force. So that's a series of approximations that are made to simplify the system. As you make these simplifications to the system, you gotta be obeying the laws of physics. So mass conservation and energy conservation, angular momentum conservation are very important for models that are run on long time scales. So as you do these approximations, you have to make sure you do your math to make sure your continuous system conserves those quantities. I won't go into more details about that. I just want you to be aware of that. You need a consistent system. In terms of the vertical coordinate, almost all global models use what's called a terrain following coordinate, which simplified the boundary condition with the surface. So basically you say, if you're using pressure coordinates, you can also just use Z. You're basically saying that the lowest model level just follows the topography as depicted up there. It's called a hybrid coordinate because as you get higher and higher up in the atmosphere, you basically slowly move into just constant pressure levels. And you do the same thing in Z coordinates. If you're using Z coordinates, which is like what MPAS is using, you go up, when you go up in the atmosphere, you just transfer to constant height levels. But the dichrome you're going to use here uses pressure. Another very popular thing to do with the vertical coordinate is to let them float. So that's called a Lagrangian coordinate. So that means, if we just think about pressure coordinates, if you have convergence, so air flowing into a cell, the cell will expand because you have more mass. Then you let your vertical coordinate just follow that. It's Lagrangian. There's no flux of mass through it. So like if we let it evolve, we let it evolve for how long do we let it evolve? We'll let it evolve for 15 minutes. So then you'll get these disturbed layers or perturbed layers. And then every 15 minutes, we'll then remap back to the model levels. Because if we just let them evolve, they'll start to really curve over and the model will go unstable. So that's called a Lagrangian vertical coordinate. It's used as GFDL. It's used here as well. The advantage with that is that your numerical method becomes 2D instead of fully 3D, so you can have faster solvers. Okay, if you're not an atmospheric model and not into this kind of stuff, don't worry too much. I just want to show you what the equations of motion look like here. So we have momentum equation, thermodynamic equation, and then a mass equation. So those are the equations we are solving in a Lagrangian vertical coordinate. We do have water in the atmosphere, and water can take a lot of different forms. And again, a lot of model makes a lot of different assumptions here. So in a cell of air, you will obviously have water vapor, which is a gas. But then you also have condensates, which are not gases. So that could be cloud liquid, cloud ice, rain, grapple, whatever forms. If you let the microphysics people go crazy, they'll probably add even more to them here. Common thermodynamic assumptions, we assume the atmosphere is an ideal gas. We assume condensates don't take up any volume. We also use constant latent heats for phase transformations in the model. One thing to be aware of is in these large-scale models, we don't have separate momentum equations for each component of water. So there's not a separate equation for grapple or snow or ice in the model. So that means they all move with the same large-scale velocity. They all have the same temperature as the air in the cell. And then the parameterizations will then be responsible for moving things between layers and so on. If you're interested in this subject, a big group of us published a paper on these kinds of things back in 2022, but it's 80 pages, so good luck if you want to read it. Other dynamical core considerations, you need a grid. Again, the last 20 years, we've tried to move away from that long grid to all kinds of fancy new grids to make it easier to implement on a parallel supercomputer, so reduce MPI communications. You have to choose the discretization method as well. You have to choose an order of accuracy. You kind of have to balance computational cost with accuracy. You have to figure out your arrangement of variables. Like, do you define all your variables as cell centers? Do you put the winds in the faces of the cell? And so on. You also have to pay attention to mass and energy conservation in the system if you're running long time scales. And again, for atmospheric modeling, the transport operator is very, very important. It needs to produce physical, realizable solutions. So your transport scheme should not produce like negative mixing ratios. They're not physical. You don't want them to do overshoots because you might have water vapor condensating just due to numerical errors, et cetera, et cetera. So we have a lot of constraints on that. A lot of people have spent a lot of their careers trying to develop methods like that. If this is of interest to you, we had a colloquium here in this room back in 2008, and all the lectures are written up in this book, and it's basically all the deliberation you go through to build a global model. Of course, a lot of stuff has happened since then. I don't get any money if you buy the book, by the way. We also have what's called DCMIP, Dynamical Core Model Intercomparison Project, that we started back in 2008. We've been running on a presidential cycle every 4 years since then, but then COVID interrupted it, and funding is getting harder, but it looks like we're going to have one in 2030. So please apply if this is of interest to you. It's really fun. We have a lot of modeling groups coming in, running idealized tests, and do a lot of fun dynamical core stuff, and we have also expanded into machine learning now. Okay, so now I'm going to provide some details on our new default dynamical core in CESM 3 or CAM7, if you will. It's called SEC-SLAM. It stands for Spectral Element with Conservative Sim-Lagrangian Multi-Tracer Transport Scheme, so SEC-SLAM. It's based on a cube sphere discretization. I like to think of it like this. You take a sphere, you put a Rubik's Cube in there, and then you inflate it. So it comes out and spans the sphere, and that's pretty much what you see there. For those of you who are into this kind of stuff, this is a mnemonic equiangular discretization, cube sphere discretization of the sphere. The nice part about that is, each panel becomes this basically Cartesian mesh where you're solving your equations of motion. The 1 degree model here will have 30 times 30 elements on each face here. You're going to be running the 2 degree version, so you'll have 16 times 16 elements in there. This was all made with Claude. I'm just blown away. I just told it. Well, it was a couple of iterations, but still, I find them really nice. And it would have taken me like half a day to make them. Anyway, on the right side, you see each element here has this Gauss-Labato-Legendre grid. So that's a computational grid. We're using what's called a Galerkin method. So it means inside of each cell, you represent the solution with Lagrange polynomial. And this grid here is a quadrature grid, meaning that's what we use to do mathematical operations on the basis function. So gradients and divergence operator, vorticity, and so on happens in that space. And just to show you here how this stuff works in 1D, let's just assume we have a distribution. Let's say it's water vapor, a nice smooth solution here. It's representable by our basis functions here. So there are no kinks in this curve here. And you see all the 4 points here inside of each. Those are all the elements. So you see 3 elements in each of these. Then we go to B on each element. So now in each of these guys here, we advance our dynamical core solution 1 time step. So whatever you want to use, we use 5-stage Runge-Kutta for those of you who are into numerical methods or familiar with them. But now, the solution in each element has evolved independently. You see these 3 different polynomials here. So what we then do afterwards is we do an MPI communication on each side of the element, and we make the solution C0 meeting. We'll make sure they have the same solution from the left or the right. The derivative is not continuous, but they meet at the point value there. That's just a very, very brief overview, just to give you an idea of how this dynamical core works. To make it even more complicated, we solved the dry equations of motion on this quadrature grid, but then we do tracer advection with a different method, a finite volume method. We do that because finite volume method has so many nice properties for tracer advection. Spectral elements has really nice properties for solving Navier-Stokes with a higher order method. So we're like trying to combine the best of both worlds here. So tracer advection, just to give you a little bit more insight into that, here's a schematic showing what an Eulerian flux form discretization looks like, and on the right, what a Lagrangian one looks like. If you start looking at the right one there, so what this method does is that you track areas moving with the flow. So you can consider it somebody throwing out their fishing net, you know, and then after one time step, it ends up in the grid cell exactly as a square. So it's like shown up there. There's no mass flowing through the sides of that cell. So the prediction equation is very easy. The mass that's over that gray area ends up in the mass that's shown in that violet area up there. That is the equation we're solving for mass conservation. So all the bells and whistles of transport scheme is how do we find the solution over the gray area there. That's the Lagrangian form. On the left-hand side, I've shown the Lagrangian form, but on top of that, shown the Eulerian form. The Eulerian form, you don't move with the flow. You stand still and you observe how much water or how much mass comes through each cell wall. So you see each of those yellow areas, that mass is swept through each cell wall. So the transport scheme we're using, it can be cast in both forms. In the model right now, we use the left-hand side here. So all the bells and whistles of the transport scheme is you have to do a reconstruction, and you have to integrate or simplify these yellow areas to figure out what is the mass flux. So we have a lot of grids flowing around here. Apologies that it's a little more complicated than it could have been otherwise, but this is the model we're using. So when you're running the model, you'll see NE16 PG3. So I know that's very cryptic, but the NE16, that was the number of elements in each phase. The PG3 refers to this CESM grid, which also happens to be where we run physics on. So when you output anything from the model, you don't need to know about all these other grids. You only need to know about the PG3 grids. That's where your output comes from. That's where physics is run. We pioneered this method here at NCAR with DOE funding and base funding. We also looked into running physics on a lower resolution grid or a higher resolution grid. DOE has adopted the lower resolution grid in their quote-unquote operational system, and other modeling centers are also looking into this. And the nice thing is when you do PG2, you run physics in 4 cells instead of 9, so you speed up physics by 5/9. Alrighty, so the vertical, I gotta finish up here. So the vertical grids here in CAM have changed. So we have been stuck with a 40-kilometer top for a couple of decades. We only barely changed the vertical resolution from, I think it was 28 to 30 to 32 over the last CAM 4, 5, 6 versions. A big upgrade this time, making the model a lot more expensive. We have increased the boundary resolution, which is shown on the right-hand side there. The CAM 6 is our old model, and then the green line is the new vertical resolution. So you see the lowest level have moved down to 20 meters, which caused havoc in some parameterization schemes. So we had to make a lot of modifications, especially for the deep convection scheme. So much higher resolution in the boundary layer, but then we also moved the model top up to 80 kilometers. So we have a well-resolved stratosphere. So we now have a free evolving QBO in the system, the quasi-biannual oscillation, if you're into that kind of stuff. But we have retained the low top version, which I think you're going to be running. That's the LT, the 58 level model version, because not everybody wants to pay the price for a resolved stratosphere. Okay, So we have a history at NCAR to have a lot of dynamical core and enabling dynamical core research. It's very unique that we have that. I don't know of any other modeling system that supports this. A reason to support this is that we always want to know the sensitivity to the dynamical core in a climate modeling system. We want to assess errors in the system. So that's a reason to keep them in there. But also, what's best sometimes determines on what compute platform you have, what's most efficient, and so on. So our old dynamical core, we got rid of our spectral transform dynamical core a couple of years ago. And then our previous default dynamical core was called finite volume, originally out of NASA, then out of GFDL. They then make an FV3 version that's in there. It's not that well supported because funding ran out. Then our new default for 1 degree application is SEC-SLAM. We have a project called StormSuite where we're bringing in the non-hydrostatic solver from DOE with C++, Cookus, with your question about codes. So that's very high end in that sense. And then we also have the MPAS dynamical core from our colleagues across town. M-Cubed laboratory, and that's the one we use mostly for our 3-kilometer applications because it was developed for weather, so the die core works really well at 3 kilometers. Alrighty. On Friday, my colleague Adam Harrington will talk about variable resolution applications that have become very, very popular. The attraction here is that you can run at a high resolution in an area over the globe, just make sure it's not too big, a lot cheaper than running globally uniform resolution. So here is some eye candy of different grids. It's mostly focused on spectral elements because that's what we have the most experiences for climate applications with regional refinement. But there's like a grid down to 10 kilometers over Greenland. When we do that, the surface mass balance of Greenland vastly improves because now we're resolving the precipitation processes over Greenland. So that's had a lot of success. And remember, this is enabled in fully coupled CESM. It's not just atmosphere only. And then we have the CONUS grid, the third one on the right, also very popular, high resolution of a contiguous United States, and then one over the Himalayas. He'll talk more about that. I think it's safe to say that the dynamical core problem associated with variable resolution has been solved. The die core deals well with this. We don't have any spurious noise as you go in and out of these refinement regions. But please be aware that a grand challenge is to have well-behaved physical parameterizations as you do that. In particular, convection. It's like you're resolving convection in there, but not out there. How do you make it slowly turn off? So that's really hard, those kind of parts. I want you to be aware of that. The other thing is we tune the model at 1 degree resolution. It's a huge effort to tune a 1 degree model. We tune in coupled model setup, optimize it for that. We do not tune in AMIB, meaning in force setting where you specify the SST. So you're not getting the best model in AMIB setup, but you are getting the best we can do in coupled model setup. So it's tuned at 1 degree. That doesn't mean it works well at the higher resolution. So you should be aware of that if you venture into this world of variable resolution. Okay. Sophia is not getting angry yet. So just want to mention, and I alluded to it before, so CAM has a model top at 42 or 80 right now. That's low top, mid top. We also have WACOM, for which there is a lecture later in this week. That's the model top is up in the thermosphere at 140 kilometers. And then we also have geospace, that's WACOM X, where we go all the way up to 600 kilometers. And from a die core perspective, that is challenging because now you have to represent thermoconductivity, molecular diffusion in the die core, so you need to add those things in there. You also have species-dependent air up there, so a lot of changes that goes into the die core to run the model up there. And that's where you really need a deep atmosphere approximation. You're approximately making a 10% error in the die core if you don't have a deep formulation. And there is a a version of MPAS being developed for deep atmosphere, and there's also a version of the spectral element non-hydrostatic at DOE doing the deep solution. So there's still a lot of research going on in dicores. Okay, you can read this on your own if you're interested. That's all listing all the bells and whistles about non-hydrostatic dicores. And then I'm ready to take questions. So. Yeah, go ahead.
Hiya. Are we also working on Wacom 7? So, yeah, the new one for CSM 3, or because I didn't ever see you've increased the top to 80 kilometers. Thank you, by the way. That's awesome. So I would probably be transitioning to Cam 7 rather than Wacom. But are we also working on the Wacom 7?
If we are working on it, or if you are?
Sorry, not we. You.
Yes, and it's a tough one as a dicore person because it's so hard to stabilize when you go into the thermosphere. But yes, we are working on a Wacom 7 model. That one we're developing both at 2 degrees and at 1 degree. It's a quite expensive model. So yes, we will release a Wacom when we release CESM. But you pointed it out that MT can now do a lot of the jobs that Wacom used to do. So for some cases, people can switch to the MT model instead of Wacom. So yeah.
How long will it take if we run the Cam 7 for 40 years or 50 years? How long will the model?
How long we run it for?
Yeah.
In terms of coupled model, the very minimum we run 20, 30 years. But we care a lot about tropical oscillations like the ENSO oscillation and so on. And there you need at least 80, 100 years to really look at that. And when you're running with a fully active ocean, we try and keep spinning up the ocean, but it takes a long time to equilibrate. We're talking, if we could, we would run 1,000 years to spin up the ocean. So in that system, you really have to run long time scales. But then again, if you're just looking at precipitation biases in the tropics, they tend to build up really fast, then you don't need to run as long. But if you're looking at anything at polar latitude, so surface pressure patterns or something like that, you need to run quite a bit longer to get a good signal. So it really depends what you're looking at. And then we have the Wacom folks who care a lot about the QBOs that need to run at least 4 or 5 QBO cycles to get a good signal. So yeah. People need more coffee. Yeah, go ahead.
Yeah, compare with physical parameterization such as a cloud, I personally think the dynamical core seems to be much more solid and have a less uncertainty. So what is the major remaining question in developing the dynamical core?
Yeah. In some sense, I could agree with you. In some sense, not. If you just tweak a parameter in the convection scheme or the turbulence scheme, you can really influence climate. In the dicore, tweaks are much more subtle. So in that sense, you can say, and most people don't care about the dicore, they just want it to be fast and not blow up. So for processes that are dominated by the parameterizations, obviously the dicore doesn't play much of a role. But for processes on longer timescales, such as if you're looking at stratospheric vortex or so on, all of a sudden the dicore becomes quite important in maintaining all the thin filaments you have in the stratosphere, so you need high order methods for that. When you talk to the chemists, if you have errors in your transport scheme, that shows up, but it's very subtle and you have to look carefully. So a lot of these dicore things, you have to look closely to see it. If you just look at the mean fields for a long simulation, it's not as important. That said, it's a little depressing that you go in and develop a high-order dynamical core, and then you throw it over to physics, where a lot of stuff is just first order, or even the coupling between dynamics and physics is first order as well. So you could argue there's a catch-up we need to do to maintain higher-order dynamics. We also need higher-order physics, which would require higher-order coupling between the two. Unfortunately, that becomes very expensive. And in the past, the software has also been the limitation as well, that it's very hard to implement. But I think that's changing very rapidly now.
You mentioned that the vertical layers, they evolve for 15 minutes before they're forced back to their original setting. I was kind of wondering if that 15 minutes is like a set number irrespective of the time resolution of like the model, and what the motivation behind choosing 15 minutes is.
Yeah, so if you look at the dynamical course solver, there's a lot of subcycling. So we basically determine a physics time step, and then we work backwards from there. In climate modeling, we have a ridiculously long physics time step, like half an hour. That's a long time. But physics is also very expensive, so if we do decrease the physics time step, the model gets more expensive. But I would definitely like to have the time step to be a lot shorter. What we then do from there on is, okay, then we need to find out what is our vertical remapping time step. And we want the model to be as efficient as possible. And the main factor there is basically the stability of the transport scheme. So when we're running with the CESM transport scheme, we're basically running at the stability limit with 15 minutes. So that means we run just one tracer transport time step, and then we do vertical remapping because we don't have the capability of running a time step for tracer advection longer than the vertical remap. So in that setup, like, there's no other choice than just doing it every 15 minutes. But if you're running, like I have run the model with simplified settings with just one remap. And speaking of sensitivities to the die-core, I had the model running, actually the full model was actually running with it, and the clouds responded strongly. So that means that we only remap once every 30 minutes instead of twice, meaning there's less numerical diffusion from the vertical remapping. And that had a big effect on clouds. But that's one of the, I was surprised, because usually it doesn't matter, because if I go from 2 to 3 to 4 vertical remappings, there's very little sensitivity, but the 1 to 2, there was a lot. So,
Does that happen on like a smaller time scale? Does it still, like, does it show different sensitivities towards that?
yeah, in the physics, yes. So there's a sub-cycle between the boundary layer scheme called Club and the microphysics scheme called Pumas. They are in a loop together, and I forget how many times, but they have to respond on very short time scales. The downside is that the die-core doesn't see that and doesn't respond to it. So there have been, especially with the FV3 dynamical core, that they have moved in fast processes from the physics into the die-core as well, so you can get a rapid response from the die-core to these kinds of processes. So that's really an area where, personally, I think there's a lot of room for improvement, is to try and get things more in sync, because when you go into the die-core, you either dump all the physics parameterization tendencies in one go, or you can dribble it in, and then the die-core is like out of whack, and die-core will always try to get back into geostrophic balance, and as it does that, it emits gravity waves. So it kind of like evolves into its own state, and then poof, it's a constant back and forth. And high-order methods do not like all that poking. So we have to be very careful that we don't introduce noise when adding the parameterizations. So yeah, that's a good question.
Okay. Unless we have a burning question. No. Thank you, Peter. Okay. Now we're going to have another 15-minute break with a light snack and return at 10:30. Hello. Okay, hello, welcome back. Next, our next speaker is Rory Kelly, who is a HPC consultant in the Computational Information and Systems Lab at NCAR, and he'll be talking about HPC resources.
All right, morning everybody. All right, so I'm Rory. I'm a part of the consulting services team here at NCAR. So our group basically does computer support for software and services on the supercomputers. You will interact with one of my colleagues this morning in the first lab session, and then I'll be in the afternoon's lab session helping out. So you'll get to meet a couple of us today. I'm going to basically just talk through sort of the HPC resources we offer here, give you a little background. This is my most important slide. I'm going to start and end with it, but this is basically the root of our documentation. So if you go to NCAR HPC docs.readthedocs.io, or if you Google like NCAR documentation, you'll land on this page. And I'm going to point out just three kind of important parts of this, right? So that link there, getting help, that will take you to the consultant on duty. That's always myself or another one of the consultants is sort of on shift between 8 and 5 during the business days. So if you need to talk to somebody and want to like have a direct phone call with them or set up a meeting or even just know who's on shift to ask a question to, that link will take you to whoever's on duty. You can submit a help ticket, and this will go, again, it'll go to the same person who's on duty, but it doesn't have to be 24/7. Like we'll see this, it gets queued up, and so this is like a support ticket to ask a longer form question if you want to add attachments or put in text or something. Submitting a ticket you can do through that link, and then probably the most important thing for actually like new people and tutorial people is getting help with passwords. That's probably the biggest problem we're going to have today is someone's password isn't going to be set up right. And we're lucky because we're here, so the password help people live in this building. We can go down and talk to them. That's usually a lot faster. But you can also call this number, 497-2400, and those are the people that can help you with passwords. That's something my group, we don't have visibility into that. That's like institutional level IT. So something we cannot help with is passwords. But okay, so what we're going to cover today, just kind of the systems we have, how to use them, what they're for. Talk about how to sign in, access the systems, because hopefully you will be doing that here in a little bit. The software we offer, how to interact with the computers in terms of like running the work, scheduling a job, and then how to customize your environment a little bit, set it up. Some of this stuff is broader than you'll need for the tutorial. A lot of the tutorial stuff is going to be really specific to CESM, and this is a little bit broader, like to give you some context into what's happening with some of the scripts and things that are set up for you. At any point, feel free to like ask a question during this. I'll have a little time for questions at the end too, but yeah, feel free to just ask me a question, raising your hand if something comes up while I'm talking. Cool. So derecho, this is our big computer. It's funny. It would have been a big computer a few years ago. In the context of the last couple of years, it's a very small computer these days, sadly. And weirdly, something about the HPC marketplace, we couldn't afford to buy this anymore, which is kind of weird. We bought it like 5 years ago, but actually buying the same thing right now would be about 3 times outside of our budget, which is really odd. But anyway, we have it. It's on the floor, and you get to use it today, so it's great. What is it? So it is a dual socket. That means there's 2 processors in each one of the little boxes that make it up. Each one of those processors has 64 cores, and that makes up what we call a node. A node so then has like 128 processors, 256 gigabytes of memory, and a Cassini Slingshot 11 NIC. And in a supercomputer these days, the only real super part is typically the network, and maybe like how much memory it has or whatever. But it's all like you could go to Best Buy and you could buy most of these components. The thing you can't buy usually is the network. The network is fancy. So that's kind of the only fancy thing left is this network, the way it's connected. It's very high bandwidth, and all the nodes, even though there's 2,400 of them, they're still sort of topologically close the way they're wired together. It also has 82 GPU nodes, which as far as I know, you're not using during the tutorial, but there are 82 GPU back nodes too that we don't need to worry about too much. The other system we have that you will interact with is called Casper. So Casper is like, it's a very complicated thing. It's like it's constantly evolving, growing, morphing cluster that we manage ourselves. So it has lots and lots of generations of different node types, and their capabilities are different. So, I used to joke that Casper was so complex it's too hard to put onto a slide. And it really is. I can't do it anymore. I can make the font really, really small, but it just doesn't make any sense. So if you actually have any interest in what Casper is, you can go to that documentation link. But basically, it's a whole bunch of weird hardware all shuffled together. And the thing you'll be using is what we call like a high throughput node, which is kind of a CPU node for general work running analysis scripts. And again, you don't need to worry about the details too much because a lot of that is taken care of for you by the tutorial scripts that are put together. Okay, so how do you get on these systems? So we use Duo authentication, so two-factor authentication. Hopefully you have all or most of you have walked through the Duo process at this point, getting it set up. But for all the services we offer now, I don't think there's anything outside this window anymore. Everything authenticates the same way through Duo. So as long as that works, you should be able to do everything you need here computationally. So it's a two-step process always, right? So you enter a password, you pull out your phone, and you wait for it to go bing, and then you approve the process. The only thing that does sometimes happen in the library during these tutorials, the Wi-Fi in the library often can't handle like 80 to 90 people getting push notifications all at once. So sometimes they get slow, and you won't see a notification, and then you're like, oh, is this thing working? Sometimes it takes a long time, and like it times out by the time it actually shows up on your phone, the notification's not good anymore. That's a common tutorial thing. So there's a second way to do this. You can alternatively, instead of entering your password and waiting for the push, you can enter, if you open the Duo app, there's like a little rolling code for the in-car authentication piece. So when you get to the screen, you can enter your password, and then a comma, and then that 6-digit code, and hit enter, and that skips the push notification. So that's sometimes helpful for these tutorials. And like I said, my colleague will be floating around the first tutorial, so you don't necessarily need to remember that, but she can walk you through that if pushes get slow. Okay, so the way I live, being an old person, how I access the computer is through the terminal. I live in the terminal still. This is the most basic way to access a supercomputer, usually by SSH. So hopefully you have some terminal software on a local system, on your Mac or your laptop that you'll be using today. And you would SSH to, for derecho, which you'll be using today, you would say SSH-L, your in-car username, and then derecho.hpc.ucar.edu. Another syntax is you could say SSH username at derecho.hpc.ucar.edu. It'll be the same for Casper on Thursday when you get to it. That derecho is an alias for 8 different login nodes, so it just kind of balances traffic between 8 login nodes. And we'll send you to hopefully the one that is less busy. So what it'll look like, you pull your phone out, you'll get the yes, no, approve, deny little dialog box after you've entered your password. You click the approve, and then the login process in your terminal should complete. X forwarding is something that you will probably do. This gets less relevant every year, but I know we still do it for sure for parts of the tutorial. X forwarding is basically like a graphics package for Unix that was invented in like the late 1960s or early 1970s. I don't know, I'm not a historian, but it's super old. During the time that I've been involved in computing, it's never worked well, and it still doesn't. But there's still a lot of X software out there. So to enable X forwarding from your laptop, you need to have an X terminal installed locally. So some of you may have done that, installed X11 or X Quartz locally on a system. And so to forward an X connection, you do this SSH-XY username at. You'll notice in red here, this time I've got a number after the derecho.hpc.ucar.edu. That's now logging into a specific login node. the reason I've done that here for the X11 forwarding, there's a weird thing with Macs. Sometimes the display forwarding doesn't work on a Mac XQuartz terminal if you use that derecho.hpc.ucar.edu. It gets lost somewhere in the round robining of DNS. So if you specify a specific login node, that will sometimes clear up the issue on Macs. But I'm going to also tell you, you don't need to worry about this too much because I've got a better way to do X later. Okay, I'm going to fast forward through a couple slides. You'll see why in a minute. This is an old way of the improved way of doing X called VNC, but it was still kind of complicated to set up, so ignore that. This is an old way of doing another way called FastX, which is like an improvement on the X protocol, but you can ignore that. We don't do that anymore. I still have those slides because they do still work, so if you want to try those, it's possible. But we have a new thing this year called Open On Demand. And all of these services now you should be able to do through Open On Demand. You should be able to authenticate just with one Duo sign-in, and once you're in, you should be able to run any of these things without any additional authentication. So for this, you'll go to ondemand.hpc.ucar.edu. You will sign in one time, Duo push. It'll get you down to the landing screen, which looks like that, which I'll now blow up. And so Jupyter, VNC, and some other tools will be available from here. Jupyter is what you're going to use probably pretty heavily, I would imagine, on the Casper day. But also the VNC desktops to display interactive graphics are easy to launch from here too. So as you can see, like for me, recently used apps, these show up. If this is your first time logging in, those might not show up right there. So you would go up to the menu up here under interactive apps, and they should also show up in that drop-down menu. And then for Jupyter specifically, you'll be requesting some resources. The specifics of that should be in the tutorial. I think probably the only important part will be this box here where it says, queue or reservation. That'll be called tutorial on the tutorial day. You'll want to select that. But if you don't select it, it should still work. It might take longer for your resources to get spun up. But you would fill in these boxes. You'd say, I want to be on Casper. You'd change that. That's my code, but you would change your project account to the CESM project code. Details of how many nodes and things you would want will be provided in the instructions, and then you click the blue button on launch, and it will start going and getting resources for you. And once the resources are available and your job is running, you get a little button down here, connect. You would click that connect button, and it'll take you into a screen like this. This is Jupyter. Probably a lot of you have used it in some context at this point. You'll get to the Jupyter screen. So probably don't need to go into a great detail about what Jupyter is, but a lot of interactive sort of Python displaying, graphing, data analysis can happen in that context. So hopefully this is all seamless this year. The only caveat is I think this is the first year this tutorial is the first tutorial we've ever taught using Open On Demand version of Jupyter. So we'll see how it goes. It's fun to be the guinea pig sometimes. The other thing that I mentioned you can do through here is start these VNC sessions. So that is like if you just want to be able to navigate files and like double click on a picture to open a picture of a plot, it's nice to have these VNC sessions. Again, if you're logged into Open On Demand, you won't have to do any further authentication. Now you can just click on that VNC button. And same thing, you'll fill in a little bit of information about what resources you want, but it'll eventually launch you into basically a virtual Linux desktop. And this desktop will actually be running natively on Casper and then just displaying back in a window in your browser. And so that'll give you full X11 compatibility to click on files and open all the X programs and all that stuff and get GUIs natively. Okay, so some basic just guidelines for accessing these systems. They are shared, right? So those login nodes, the 8 of them on Derecho and the 6 on Casper, are things that not just you guys, but then maybe around 1,000 other people are using throughout the day. So we do try to limit the amount of stuff you do on there to kind of reasonable interactive things. There are places where you might want to go to, it's okay if you want to compile a short amount of code, like a little build or a serial build, or if you want to run a short script, that's all fine. But you wouldn't want to try to run CESM itself on a login node. You wouldn't even really want to try to compile CESM on a login node because it takes too many processors and it takes too long to do it, and it would make the login nodes unresponsive for other users. So basically, we want you to sort of read and edit code, compile little programs. You can do some data transfer there, like SCP files around or copy files from one system to another, totally fine. And then the main thing, therefore, really in terms of running work is interacting with the job scheduler, which I'll talk about in a little bit. If you do something on a login node, like that's too resource intensive, we have some automated processes that will start to sort of limit your resources. They'll basically throttle down the amount of CPU and memory you're allowed to use to the point where your own experience will become pretty unpleasant trying to do things. And we'll get an email that'll say, you'll get an email, and we'll also, we the consultants will get copied on it saying, you know, user so-and-so is doing a bad thing on this login node, please stop. And you're not gonna hurt anything, so I mean, like, the computer's not gonna crash and die, hopefully. But you will get a nasty email asking you to please move your work to a compute node if that happens. Okay, so data storage. We have a few spots that are good to know about, particularly if any of you are, after this tutorial, going to be working on other NCAR projects and having accounts here long term. It's kind of good to know what these spots are used for. So the first one is your home directory. It's not huge, it's only 50 gigabytes, but it is backed up, and it's backed up sort of hourly throughout the day. So if you keep important work and scripts, I mean, important code, scripts, all that stuff should be in version control, Git or something anyway. But you can keep important data, stuff you're working on in your home directory. And if you do something silly like accidentally delete it, we will have backups of everything in that space. So put important stuff there, but it's a small space, so don't like dump a whole bunch of output data that you could recreate if you needed to. Don't put it there because your home space will fill up. A better space for that is what you would call your workspace. So that's in, and I guess I should mention this /glade in front of all these paths that I'm mentioning. GLADE is an acronym for the Globally Accessible Data Environment, I believe. So everything starts with GLADE. It's visible from all the systems we have here. And these spaces are common. So Derecho, Casper, they all share these spaces. So your workspace, which would be in GLADE work and then / your username, it's a much bigger space, so it's 2 terabytes. We don't back it up, so if you delete something out of there, I'm sorry, but it's gone. However, we don't delete things by surprise, which is nice, because we have another place where we delete things by surprise. So things I would put there is like your compiled builds. You build the CESM model. That's a great place to store it because it takes up a lot of space. You don't want it in your home directory all the time. And we won't delete it. It can be there as long as you want, and you can fill up that 2 terabytes with whatever you want. And if something important ends up there, just make sure you have a backup somewhere else because we don't back it up there. The third space in Scratch is much bigger, so 30 terabytes. This one, as the name Scratch would suggest, is meant to be temporary, so not long-term storage. And we do delete things out of there. I think right now, every 120 days, if you haven't accessed a file, we'll delete it after 120 days. And a lot of things will just disappear. We don't tell you like, oh, we're about to delete this. It'll just be gone one day if you haven't used it. So don't ever think of that as like a place to keep stuff. That's only like, as you're working, store stuff there, but then anything that's important from your work, move it somewhere else, or it's gonna go away. And then campaign is another space you don't need to worry about too much, but it is like if you are involved in an NCAR project long-term with another PI, you'll get an additional space that's kind of project allocation that you can use later on. So moving data to and from the system, so copying between any of those file systems is pretty easy because they're all kind of local and native to each other. For big transfers like from your home institution to NCAR or from NCAR back to your home institution, we tend to recommend Globus. So if you like work at a university, they likely already have what's called a Globus endpoint. And you basically log into Globus. You can authenticate a couple different ways, like institutionally if you have an email account, or you can create a new account. But basically, your home institution will probably have an endpoint. NCAR definitely has an endpoint, and the path between those 2 endpoints is very fast, typically, much faster than using like SCP or CP or something like that to copy files. So if you're moving like a terabyte of data, definitely do it through Globus. Don't do it some other way. Feel free to, I mean, that's a very high-level overview, but feel free to ask questions throughout the week if you do want to like move some output data or something back to a home institution at the end of this week. Let's see. Oh, environment modules. So the way we kind of, the way we recommend to manage your software environment on these systems is through a thing called modules, and that's basically and pretty common. If you've had an account on another university or institutional system, modules is pretty common these days. It basically is like a list of software that within the environment it's loaded in should all kind of work and play nicely together. So it's organized in a hierarchy where it's like the base of the hierarchy is kind of like the compiler you're using. You load a compiler, and then all the software that has been built and guaranteed to work with that compiler shows up once you load a compiler. And then additionally, MPI, which is like a network communication library, that's another important piece. So once you load an MPI library, subsequent software will open up. So basically, like each step, you're loading some new software. It gives you new options of things you could load that depended on what you just did. And end to end, it kind of guarantees the environment you have loaded is all consistent and able to work together. Whereas these files all do just live on the file system, you could go out and find these libraries and link them together randomly in your executables, but they wouldn't all work together. So that's kind of the point of modules. You don't need to know too much about it, but I have just a couple layers here: compilers, debuggers, MPI libraries, IO libraries. All those things start showing up as you are. Yeah. Okay. Gotcha. I thought you had a question. I was like, well, that's odd. Sophia's been here before. Okay. So the way you interact with the system is going to be, through your laptop to one of those login nodes, and then from a login node with the batch system, which, again, you don't need to know a ton of details, but these are probably the commands that you will be interested in. qsub is going to be done for you by the CESM scripts, but that is basically submitting a job. So it's good to know that exists because that's happening for you behind the scenes. qstat you will probably use. That's saying, what is the status of my job? Is it running? Is it still queued? qinteractive, if you want to get a batch node just to interact with that's not like a scheduled job, but you can have a terminal where you're typing, you can use this qinteractive-a your project, and that'll start an interactive shell for you. And then something else you will be using is this qcommand or qcmd. Again, qcmd-a, whatever your project is. For this week, it'll be the CESM tutorial project. And then 2 dashes, and then any command. And so whatever that command is you put on the line after the 2 dashes, if you've done the qcmd with a command, it then takes whatever that command is and ships it off to a batch node to be run for you, and then the results are returned to you. This is what a batch script looks like. Again, it's just good to know these exist because the CESM scripts kind of wrap all this up for you. And so you, for CESM anyway, don't need to interact with these directly, but these things do still exist, and CESM kind of manages and creates them behind the scenes. More on modules. Okay, back to my most important slide. So like I said, we'll be floating around throughout the day today in your labs. So if you have questions, come up this morning. It'll be Mia, my colleague in the workshop, and this afternoon I'll be back myself. Feel free to ask us questions, and if we're not around later in the week, you can use any of these links to get a hold of us. And questions if you have them. Question, yeah.
So you mentioned using open on demand access to
Yes. Yeah, so the Jupyter Hub you found, the other one, is the old way, and it still exists for compatibility, but we're going to deprecate it sometime this year. So yeah, I would recommend not using it. If you're starting now, just use Open On Demand because it'll keep existing. Yeah. Mhm. No, VS Code is great. We do see there are some plugins with VS Code that can start hogging resources. Like a lot of the plugins are written for single user systems. And so you'll get something that tries to consume all the memory or use 16 processors at a time. And so VS Code itself will start triggering those nasty emails I mentioned to you. Like you might get an automated email from the system saying, you're doing a bad thing on one of the login nodes, please stop. And you're like, well, I'm not doing anything, but VS Code in the background is doing something crazy. So we see that from time to time. I mean, if that happens, it's not the end of the world, but we'll just tell you like, hey, please don't do that. There is a way inside VS Code to triage which of the plugins is causing the issue, and then you can remove it. And if that happens, you can help it. But yeah, but generally, I mean, a bunch of us interact that way with VS Code, so it's a fine tool generally. We do also have some instructions, like if you want to use it to do heavier work, you can forward the VS Code connection to a batch job instead of doing it on a login node. And you can search for that in our documentation. Yeah.
data that will be purged like in 60 days, I guess. Do you allow like a touch that prevent it from?
No, we don't. No, we don't. In fact, we have scripts that monitor for files that have been touched, and you'll get another nasty email if you start touching them. So, you know, it is like, we don't really care. But the reason we do care is because it's a very coveted space and we run out sometimes. And if we, like, as it gets fuller and fuller, like right now, I think it's 120 days we delete your stuff. But if the file system starts to get full, like now it's 60 days, now it's 30 days. And like, if it got really, really full, we'd have to tell everybody like, hey, your stuff's only gonna be around for 24 hours. So we're trying to balance that, the total amount of space with the total user community and make that retention period long and not have to reduce it, so. Yeah, it's again, one of those guidelines, just like be a good neighbor and realize that other people are using the file system. If you have a problem where you're like, I temporarily need a lot of space, email us and we can give you, scratch extensions, make it a little bit bigger or a little bit longer. But yeah, we try to encourage you to stay within the guidelines.
Thank you.
Yeah. Yeah.
We have designed the account to access the director, but after this tutorial, can we still log in that?
I think your account lasts for, what do you guys, people, I think on our side, the account exists for a month after the project goes away. So the project will go away shortly after the tutorial, and then like your account will still exist for a month, and we back up your account. However, this is a common thing, is like, you're gonna be working with someone at NCAR on a project after this tutorial. Just let us know, and then we can make sure that we just keep your account around, as opposed to deleting it and then creating another one for you in 2 months or something. We're happy to like continue that. The thing you'll need for us to keep it around is basically say, like, this is the project I'm going to be on starting later this summer, and the PI is this, and the people will email the PI, and as long as they approve it and say, yes, this person's gonna be on that account, then we can just keep your account around.
Can we request account by ourselves later, or?
Yeah, there's small startup allocations, which are basically, those are available to anybody that want to just sort of do like a proof of concept work. But long term, if you want to have a big, long running project, it needs to be an NSF approved allocation. Again, in our documentation, there's links to, submit a big application for an allocation. But the startup allocations, if you just want to like do a proof of concept, are available to anybody all the time. Yeah.
Do the consultants just help you with NCAR computers, or if we wanted to port, for example, to our own supercomputer, could you guys help out with that as well?
We do, on occasion help with that. It kind of depends on, how familiar we are with what you're trying to do and or the other institution. A lot of it, like if you're another institution like TAC or something that we also know quite a bit about or have, connections with people there, we can definitely help. If it's a university computer that we don't know much about or we don't have accounts on, then it's often hard just because we ourselves would have to get accounts created and to log in and help you do all that stuff. So, for CESM in particular, though, if that's what you're thinking, there is actually a section of the tutorial that's specifically about how to port CESM to your, there's not, oh, there used to be. It's gone. Sorry. You could maybe check in last year's notes, I don't know. There are people within CGD that would be better, within the CESM group that would be better to talk to you about porting CESM than us. But we could definitely assist with like the basics, sort of like compiler, NPI, system software stuff. But the model itself, like numerical correctness validation, that's useful.
We removed the porting section just for this year's materials because we're focusing on CESM 3 and it's not actually officially released yet, so we can't be porting the code base. But yeah, you could check, if you just add -2025 to the CESM tutorial, it'll show you the website from last year, and that has a porting section for CESM 2. And then also the project code that you're using for the tutorial should still be active until the end of August. So that's the timeline on that. Yeah, but thank you. Thank you so much, Rory.
Yeah, of course. Thanks, everybody.
So we have one more short intro to the lab. We're finally going to get started with the labs here. And yeah, so open, yeah. Kate Thayer Calder, who is the chair of the technical side of the tutorial is a scientist in the paleo and polar climate section, and she is going to give you an intro to our first lab, Basics of CESM. Guys hear me okay? All right, cool. I'm gonna make a lot of noise and stuff. Okay. Hi, everybody. My name is Kate. I am a scientist here at NCAR, and I'm helping to make this CESM3 tutorial happen this year. So this is all very exciting for us because this is a brand new model. You're going to hear this a lot. But let's just talk about what we're about to do in this lab. So this is your very first lab. We're all going to head over to the library over there as soon as I'm done talking. We have 3 basic goals here. We need to make sure that everybody's able to finish the prerequisites, which you could have started on before you got here, but that involves logging into the supercomputer. We are going to use the X11 forwarding today. Oh, Rory's gone already. For your very first exercise. So that's always a fun introduction to the computing systems and how they can be a little wonky sometimes. But yeah, hopefully everybody can get logged in, get your passwords working. If those aren't working, then we can get you down to the help desk to make sure that we can get you logged in, because that's very important this week. The second thing you're going to do is to check out CESM and spend a little time exploring the Duratio workspaces and understanding how the supercomputer works. And then finally, your third goal is to actually create and run your first experiment with CESM3. So this just gives you a quick overview again of the prerequisites. You need to make sure you can get on the wireless, that you can log in. I've got links here to the one-time setup under resources, but that's also linked under the first exercise once you get to that. So you need to make sure that you log in. There is a file that you have to copy into your home directory and source to make sure that you get the modules and the environment loaded correctly for CESM. And that's all under there. So if things don't go correct right away, you can expect some issues from most people. We'll be around. There's a lot of helpers. You can wave your hands, and we should be able to get you going with past your issues, hopefully. This is just an overview, again, of those find and download the Unix terminal. I'm just curious, who here is on a Mac? Okay. Who here is on a Windows machine? All right, that's a lot. They're the ones who usually have the most problems with this. I generally use a Mac, so that's good to know. All right. Goal 2, download CESM3. I just want to put all the caveats out here, you guys. This is not an official release of this model yet. This is one of the first times we've ever done the tutorial without the official release model version code, okay? And you're gonna see this, like when you check it out, it's gonna say tutorial tag. That means it's just for this week. Don't take this back and start doing your research with it. Don't take it home and write your whole dissertation with this code base. It is not ready for that, all right? So also, your early adopters, we just finalized this configuration 2 weeks ago. We've tested it as best we can, but there's a good chance that there's gonna be like issues. It's not scientifically supported. You're gonna do some practice looking at the output. Output's gonna look bad, all right? Just know, you're just gonna be like, this is weird, because it's a whole new configuration. I mean, it's okay, but it's probably not as good as the actually tuned model in the 1 degree. What we did was we created a 2 degree configuration that runs on fewer resources and runs faster, so you guys can use it quick. But it has not been vetted by the scientific committee yet. So, could be weird. Don't use it. So you're gonna download that. There's your instructions are in there. And then new to CESM3, if you guys have ever used CESM2 before, there's a manage external step. So first thing you do is clone, then you check out your tag, and then you do manage externals to get all of the extra code brought into your workspace. For CESM3, we use git fleximod because we're using git submodules for all of that code. So it's just a little bit different if you've used it before. This is a good time to explore the CESM GitHub pages. So CESM is entirely open source. And you can go onto our GitHub and you can look at all of the different discussions and pull requests and issues that are already out there. And this is where we all work together on this code base. Goal 3,
is to do your first CSM run. And I just want to go over real quick what this looks like. So inside the tutorial materials, you're going to see, well, okay, I don't have a, do I have a pointer? No. No. Oh, I probably shouldn't just randomly press buttons. Okay. Hey, there you go. All right, so this is what the web page looks like. Over here, there's like prerequisites for success, basics. You go all the way through this description down here. Eventually, you get down to your first exercise, which is the first CSM run. And the challenge, if you want to, based on all of the reading that you've done so far, just do this first blue one. See if you can get it done with that's the information in the blue box. If that's not enough information for you, totally fair. This is your very first time. It's your first day. You can get hints. So the yellow box doesn't tell you exactly what to do, but it gives you some very specific hints to guide you through the process of what you need to do. If that's still not enough information, the green box down here tells you exactly what you need to do step by step. So because it's your first day, if you're brand new to all of this, no shame in going straight to the green box. Just copying and pasting it in each time. And then if you have questions, raise your hands, ask us, we'll be around, we can answer your questions and stuff like that. So just, your level of learning, what works best for you, you have lots of options here. That's how these exercises work. So your first CSM experiment will be an all active case. So like I said, this is our brand new configuration for CSM3. B on the comp set means that you're doing every single component together. We have the new 2-ish degree spectral element global grid, which is the NE16PG3. That is a lot of gibberish, but that means that you're running basically a 2-degree spectral element low resolution configuration for all of the atmosphere, ocean, land, sea, ice, river, and wave components all at once. The default configuration runs 5 days at 1850 conditions. And then from there, you can do some small changes to sort of learn about how to configure your specific run. This way. Okay. I usually go over this really quickly because CSM has a very specific workspace overview, and this will be in the tutorial resources as well. But every model system has a different sort of workflow and workspace setup. Like Rory was talking about keeping your compiled code around, and we don't actually do that. So what we do is we check out our source code to your source root, which will be in the instructions. And then you create a case, which is another directory and another like subdirectory. We call that the case root. So those are kind of two important directories to keep around. From the case directory, we have a series of scripts that will build and run the model. And those actually create the directories inside your Scratch space, where it creates the compiled code and all the files that you need to run the model in a separate directory. And then once you finish running, it creates a 4th directory in your Scratch space for your data archive. So we don't keep our compiled code around. We keep it per experiment in the build here because the compiled code is specific to an experiment. So if that matters to any of you, that's the case here. The last thing you're going to do for this exercise is look at the results, and this is where the X11 forwarding is going to come in. So you're going to need to do that SSH-XY when you go into Duratio to make this work. And then we're going to use this tool called NCViz. And again, this is another first for this tutorial. We haven't used it before. Worked fine for me. We'll see how that goes for you. And then at the end of the day, we're going to test the new login to Jupyter Hub tool. So because the Open On Demand is brand new for everybody, and we've had a couple of tutorials in the past where we crashed the system with everybody logging in at the same time, we want to know if that's going to happen again. So we're going to coordinate everybody at the end of the tutorial today, right before we head back in here for the wrap up. And we're going to have everybody log in at the same time and see if we can break it and tell Rory. All right? So that's going to be a fun thing. Wait to hear from us, and we'll get everybody together and see what happens, all right? This is the Discuss CSM bulletin boards. This is actually a really good place for you guys to check out if you have questions. I don't know if this screenshot is what it looks like anymore. That's probably a really old picture, but the URL is still good over there. For the person who asked about porting, we did take it out this year, but this Discuss CSM has a whole section on porting your model to lots of different places, and that's a good place to talk to experts, even experts outside of NCAR, about porting CSM to their local machines. So if you have questions or if you want to see how other people have done it or other issues that people have had, this is where to go to get information about that now. And again, here's the tutorial website that you're going to go to. Notebooks, basics, start with basics overview. Actually, start with the plural because it's if you finish those, then go to this, and then you can work your way through. Okay. Oh, I finished early. That was good. Do you guys have any questions? Okay. If we don't have questions, I'm going to turn this off.
Yeah, now we're gonna all walk up to the library and get started on the first, part of the lab session today that lasts until noon. I think you should take your stuff with you. Yeah, take all your stuff. We'll give everybody the full. Hello, welcome back. So our first long lecture of the afternoon is atmospheric modeling with a focus on parameterizations. And Ben Stevens and Kanish Gohil will be giving this presentation together. Thank you.
Okay. Yeah, sounds like this is on. Okay. Thank you. I'm Ben Stevens. I'm going to start the talk by just going over some background about parameterizations, and then I'm going to discuss a couple of the parameterizations in CAM, and then Kanishk will discuss the remainder of the parameterizations. So yeah, basic idea behind this talk is that by the end of it, you should have a sense of what a parameterization is and why they're important and necessary in our model. We'll go over some of the most important parameterizations in CAM. And at the end of the talk, we'll give you a slide that shows you where you can sort of find more information about any of the parameterizations in the model, mainly the ones that we're going to talk about. So if you want to look at just like a definition of what a parameterization is, the AMS defines it this way by saying that it's a representation of physical effects in terms of admittedly oversimplified parameters rather than essentially fully modeling it. This is a little bit opaque, maybe. Here's a simple Wikipedia definition, although this may have been updated since the last time we gave this talk. But yeah, a method of replacing processes that are too small scale or complex to be physically represented in a model by a simplified process. So basically, in a standard run of CAM, like a 1 degree run, you're going to have a pretty large size grid box. It's going to be about 100 kilometers on a side. So that's a large area, and there's a lot going on inside of that area. Many processes that are much smaller than that area, so they could be microscopic even. And so we can't resolve those at the grid scale. We need to somehow put them into the model in a way that sort of accounts for their effects on the grid scale without actually having to resolve every little detail of that process at its natural scale. So that's the basic idea of what a parameterization is. Here's kind of an analogy. So, on the left here we have a map of Paris, or like part of it. And this Google map here, I mean, if you had your computer or your phone, I mean, you could zoom in and you could see as much detail as you want down to really fine resolutions. But maybe that's great to have if you're walking around Paris. But if you don't have access to that, which sort of the analogy here is that in a 1 degree model, we're not going to have access to this level of detail for some physical process, then the map on the right, might serve you just fine. This might give you enough information about the things that you think are important, maybe as somebody touring Paris or something, to be able to like get around the city and see what you want to see. So that's just kind of a rough analogy of what a parameterization is in a model. So yeah, basically they take the sort of really fine resolution information and try to represent it in a simplified way so that those small scale processes can be the like effect of those small scale processes on the large scale can be calculated. So there's lots of different things that we might need to parameterize in an atmospheric model. Some of them are shown here. And as I was saying, I mean, they can range from things that are, really fundamentally on very small scales, like the interaction of photons in the atmosphere with molecules like CO2 or other molecules, up to slightly larger scales like deep convection, which can be like maybe on the scale of tens of kilometers. But all of these, even deep convection, would be smaller than the grid scale, which, like I said, is about 100 kilometers on a side. So lots of these processes, like turbulence and gravity waves, radiation, clouds, convection, these things would need to be parameterized in the model if we think they're important enough to include. So factors that go into choosing, what we want to parameterize. Well, if we want to model the whole Earth, we have choices to make. I mean, the overall use of land, for example, in the land model is probably more important on the global scale than like the shape of an individual leaf. So, we might want to parameterize more generally how land is being used on larger scales. We also need to take account of computational expense. These can be expensive models to run. And if you have a really expensive parameterization that requires a lot of compute time, then that might be a drawback. So simpler can be better if you're worried about compute time. And then process uncertainty. So there are things about the atmosphere that we don't fully understand yet, and so it kind of depends on our level of certainty about what we can represent and how well we can do that. So that's sort of the first section of the talk. To summarize, basically, a parameterization is a way of representing unresolved subgrid scale processes and trying to capture how they affect the model on the resolved grid scale. And yeah, basically these parameterizations that we use, they come from some understanding of the physics that's going on, but we try to represent it in a simplified way. So we'll move on to the second part of the talk, where I'm going to continue to introduce two of the main parameterizations in CAM, and then I'll hand it over. So these are the ones that we're going to talk about: convection, turbulence, radiation, aerosols, and microphysics. I'm going to cover the first two. So convection in CAM7, you can sort of think of it as being divided into two regimes. There's deep convection and shallow convection. And these are sort of roughly handled by two different parameterization schemes. Deep convection is, well, there's a couple of differences. So scale is an important difference. Deep convection is on the scale of maybe tens of kilometers. We're talking about convective plumes that go deep into the troposphere. This is represented in CAM by the Zhang-McFarlane scheme. I think that's been in CAM for a while. It's still there with some updates in CAM7. Shallow convection, on the other hand, is smaller scale. So we're talking maybe on the order of hundreds of meters up to maybe a kilometer or so. And we're talking about plumes that would sort of be limited to the boundary layer, where there's a lot of turbulence going on. And because this is the boundary layer we're talking about, where there's a lot of turbulence going on, shallow convection and that boundary layer turbulence, those are actually both represented by the club parameterization in CAM. So club actually handles both of those. And club happens to be the part of the model that I work most closely with, so that's the part of the model I would know best. Just to give a little bit more detail about Zhang-McFarlane, or ZM as we often call it, it goes back to the 90s, but the basics behind it are it sort of calculates the CAPE, which is the convective available potential energy, so that tells you kind of how strong convection could be. And it sort of triggers based on that. So the more CAPE, the more strongly ZM is going to act. It has a convective intensity that's sort of basically proportional to K. It's a mass flux scheme, which means it's sort of based on the idea of actually moving mass up and down the column. And it has parameterized entrainment and detrainment, which means that, as a plume is rising, it can sort of entrain air with it, sort of carry along air with it, or it can detrain air, sort of lose mass to the environment. And along with that entrainment and detrainment, we take account of heating and moistening at each level. So basically, the output of ZM is basically how much heating and how much moistening is there at each level in the column, in each column of the model. So now we come to club, which, as I said, is a parameterization that handles both shallow convection and turbulence in CAM. It's a somewhat complicated scheme. It's based on the major fluid dynamics equation, the Navier-Stokes equation, which is a kind of it sort of unpacks into a complicated system of equations that model heat and moisture and winds. Club actually prognoses 11 moments, which means that it actually advances these moments in time according to this fundamental physics equation. So heat and moisture fluxes, so like heat flux and moisture flux up and down the column, momentum fluxes. So are you carrying horizontal momentum up or down the column? Variances of heat and moisture, and then covariance of heat and moisture. Momentum variances, so like momentum variances would sort of tell you most directly how much turbulence there is going on, so it calculates those. And then there's one third order moment of vertical velocity. The third order moment of vertical velocity sort of tells you how cumulus-like your column is, or how stratocumulus-like it is. So a large third order moment would be more cumulus-like, but a smaller one would be more sort of stratus, like more stratocumulus. There's a closure problem in turbulence. So in this system of equations, we have some terms that are unclosed. To close some of them, Club predicts a joint probability distribution function, a PDF. It's a PDF of 3 variables: vertical velocity, temperature, and moisture. And we can integrate over this PDF to close the unclosed terms in these equations. It's kind of complicated, and you sort of need to see the equations to get it. But it's sort of it's a way of closing those terms. There are other terms in the equations that are closed with more standard methods that go back to like the 70s and 80s. The PDF closure is really kind of the more innovative aspect of Club, I think, at least the form of the closure that it uses. So that's what I was going to talk about, and then I guess I'll pass it along now, and we'll have questions after the talk.
Hello? Oh, okay. Sorry. My name is Kanishka Gohil. I'm going to be talking a little bit about the remaining 3 parameterizations that Ben kind of sort of foreshadowed in one of the previous slides. Starting with radiation. Okay, so first of all, I am not a radiation person at all. So I'm not going to be discussing any of the nitty-gritty and complicated stuff related with the parameterization scheme, because I don't want to put my neck on the line. But having said that, CAM7 basically uses the rapid radiative transfer model for GCMs parallel, or RRT and GP, as the scheme to compute the radiation related stuff in the model. It's kind of a derivative of the original RRTMG, which was developed, I think, around 2008, 2009-ish. So it's been in the model for a little over a decade at this point. And the new scheme is rather similar to the original RRTMG, its predecessor. It has like a lot more parallelizability associated with it. It has GPU capabilities, vectorization properties. Also, a more important aspect of RRTMGP over RRTMG is that the complications associated with handling the radiative effects of gases, aerosols, and clouds, they have all been modularized. So they kind of, they're kind of calculated separately as opposed to being done all at once and then making the code structure as well as everything else like a lot more complicated than it has to be. And in essence, the radiation code supplies us with the absorption of solar radiation, the emission as well as absorption related with terrestrial radiations or long wave radiations, the heating rates, both associated with with the sensible heat as well as latent heats, and the net radiative fluxes at the surface, as well as the top of the model or top of the atmosphere. And with that, I will move on to microphysics. I know a little bit about this stuff, so feel a lot more confident talking about this. Now, clouds in general are pretty important in context of weather, radiation, precipitation, all of that stuff. And the underlying physics, or rather the microphysics of the clouds, with respect to the scale at which the clouds, of the clouds themselves, that kind of spans over like 12 or so orders of magnitude. And so these microphysical properties can't really be explicitly modeled by CAM, and so they have to be parameterized. And typically, any sort of a cloud microphysics scheme would involve the size distributions of the hydrometeor classes, the condensate phase distribution, as well as the evolution of the different hydrometeor classes that it deals with. And it does so by accounting for the atmospheric state, the macrophysics, the dynamics, and what have you. And it basically outputs some of the essential process rates, microphysical process rates, along with the mass and the number tendencies for the condensate phases that the microphysics scheme is going to be dealing with. Now, usually we would categorize the microphysics schemes into three broad categories. And without getting into too much nitty-gritty about all of this, the key point to note over here is that these mainly differ from each other in their treatments of the distribution of the condensate phases with respect to their sizes. And that kind of translates directly into how well or how accurately we can simulate clouds. So for example, the bin microphysics is usually considered to be pretty accurate, but at the expense of its computational burden, because it has way too many variables that it has to deal with. And on the flip side, the bulk microphysics is rather simplistic in its representation, wherein it only has like two variables associated with the liquid as well as the ice phase hydrometeor classes. And it's very cheap because of that, but it's not a very accurate representation of the class of the clouds in the model. And so in CAM7, what we have is something called the moment microphysics, which is like more of a hybrid microphysics scheme, in which we essentially represent the number and the mass tendencies as the properties of some sort of a functional distribution, otherwise known as moments. In this case, it's just a gamma distribution. And the default option for the cloud microphysics scheme in CAM7 is PUMAS, or the parameterization of unified microphysics across scales, which is basically a double moment cloud microphysics scheme that can calculate both mass as well as the number concentrations, or rather prognose the mass as well as the number concentrations associated with, in general, these 4 hydrometeor classes, namely the cloud droplets, ice crystals, rain, and snow. Now, this is a pretty neat and tidy representation of what a cloud microphysics could look like. But once you start introducing process rates into the mixture, then things kind of blow out of proportion pretty quickly. And we'll take a look at some of the processes which are represented in PUMAs. For example, we have the cloud droplet activation, which happens due to the presence of aerosols in the atmosphere that take up the ambient water vapor present in the atmosphere. And these cloud droplets kind of form like a feedback loop with the water vapor, because droplets can evaporate and then come back into the vapor phase. These cloud droplets also undergo something called autoconversion or accretion, which are classified as warm rain processes to form rain droplets. And then these raindrops can also evaporate, resulting in the formation of water vapor instead. Both the cloud droplets as well as the rain class hydrometeors can also undergo sedimentation, which is just gravitational settling. And this is just one half of the problem here, because this is just the liquid phase microphysics. You have the same analogs for the ice phase as well. Here you have the heterogeneous ice nucleation happening because of the ice nucleating particles forming ice crystals. These ice crystals also form due to homogeneous freezing of water vapor present in the atmosphere when the temperatures fall below, let's say, -38 or -40 degrees Celsius. The ice crystals can sublimate into water vapor. They can auto-convert as well as accrete to form snow crystals. The snow and ice crystals can also form from the rain and cloud droplets present in the atmosphere via melting and freezing. And there is something called secondary ice production, which results in the freezing of cloud droplets below sub-zero temperatures. And then these cloud droplets, these frozen cloud droplets, can then shatter, resulting in the formation of ice crystals. And then these ice crystals and snow can also sublimate. And then if we want to increase our problems further, then we can also have this 5th hydrometeor category called Graupel, which has its own stuff going on. Yeah, so that's what the microphysics is like in CAMP 7 at the moment. With that, I'm going to move on to the aerosols. And in CAMP 7, we basically simulate aerosols from all different kinds of sources. Here we can see sea spray coming into the atmosphere because of wave breaking events. You have dust storms resulting in the dust aerosols being kicked up into the atmosphere, the biomass burning events, anthropogenic emissions, and so on and so forth. And also some of the associated microphysical processes like nucleation, coagulation, wet or dry deposition, etc., etc. As the default option for simulating aerosols and the microphysics in CAMP 7, we have something called the modal aerosol model, or the double moment MAM4 in essence, which has Aiken accumulation and coarse mode simulated, as I've shown in this one plot from one of the papers. I can't remember where is it from. We also have one extra mode in MAM4, which is called the primary carbon mode. I haven't shown it here. The primary carbon mode constitutes of the primary organic matter and black carbon explicitly. And we have this separate mode in MAM4 because we want to treat the non-hygroscopic or non-CCN particles separately from Aiken accumulation and coarse particles. Similar to what we do in microphysics, this is also, like I said, a 2-moment scheme. So it prognoses both number as well as mass concentrations, mass distributions. But unlike a gamma distribution, for aerosols, we use log normal distributions instead. And in addition to MAM, we now have this new option, which is basically a sectional scheme known as the community aerosol and radiation model for atmospheres. So this is like analogous to the bin microphysics scheme or bin cloud microphysics scheme, which I showed a couple of slides ago. And the way this is formulated is that it has two groups. One is called the mixed group and the other one is called the pure group, which treats sulfate aerosols quite exclusively. And yeah, as opposed to MAM, we recently have been running some experiments with it, and it seems to be more accurate at representing the aerosol distributions as well as their number concentrations in general, at the expense of the computational efficiency. So I don't know. I mean, we still probably need to do some work on that. Okay, so with that, just the concluding slides. And hopefully, come the end of this talk, you have at least a rough idea of what model parameterizations are like and what type of parameterizations, but like at least some of the parameterizations that we are currently using within the atmospheric component of CESM, that is CAM7. And just to sort of round everything up and to help you with some of the logistics as to how to find some information on your own once you're out of the room. Then we have the CAM7 documentation. There are some of the papers. This is basically the list of some of the papers related to the parameterizations that Ben and I just talked about. The RRTMGP, Club, ZM, PUMAS, as well as MAM4. And yeah, so I think this is a pretty useful command in case someone is not familiar with this. It's a regular expression command for all of the nerds in the room. Like it's called global regular expression print. And you can essentially go into any kind of a directory within your model, run that command, for example, with the handles R, N, and I. And if you want to look up the codes or the pieces of the model where the variable cloud lick would be present, it will basically spit out a list of all of the files along with its subdirectories and the line numbers where this keyword is appearing. So it's very useful. And yeah, with that, opening to questions.
Yeah, I think you got a point at the end, like the scavenging hunt, because sometimes when I like to understand like the physical process in the model, I would like to know how the parameterization communicate each other. So that's my question. Are the parameterization communicating each other? Because sometimes the relative scheme or relative parameterization is giving out like relative fluxes, right? Or also it needs some like concentration of hydrometeors, like the concentration of like cloud particles. And I guess the radiation is asking that to the cloud microphysics. So how does that work? Because the cloud microphysics also, I think we're gonna need some information from radiation. So what is like the time step? Like which one is the first parameterization is run? Then where that information is going to? I don't know if it's a kind of general question.
Yeah. So I think the radiation code is supposed to be executed towards the end. Like that's the parameterization which is calculated the last at the end of the time step. And before that, whatever prognosis that the model needs to do regarding the greenhouse gases or the aerosol numbers or mass burdens or any of that stuff, even the microphysics, all of that has already happened beforehand at that time step, and then it's then subsequently fed on to the RRTMG, which then computes all of the radiative fluxes. Because I guess the reasoning for doing that is that we kind of want to have like a radiative balance perfectly in place as being calculated within the model. Yeah, so just to answer your question.
Across the globe, or do they vary from region to region?
They do vary from region to region.
The parameters that we have currently set in PUMAS, they are, I guess, like kind of a holistic representation what generally these particles should look like. But yes, like if you look at in situ measurements or yeah, like basically in situ measurements, for example, then you would probably see very quickly that the model parameter, for example, like if you're trying to fit a log normal distribution through the aerosol population or a gamma distribution through the hydrometeor burden, depending on different regions, the model parameters would probably vary, sometimes even quite notably.
how do you differentiate the soluble and insoluble aerosols in Model 4? So you have soluble and insoluble. Sorry, can you hear me?
Soluble. Soluble versus unsoluble?
Soluble versus insoluble. Okay. Uh, that's a good question, actually. We don't really have a direct distinction between soluble versus insoluble species. Uh, I guess for the droplet activation purposes, like when you're talking about CCN, for example, then by proxy, we have prescribed hygroscopicity for different aerosols. So like if at all the aerosol has like, let's say a hygroscopicity of anywhere between, let's say 0.1 and 1, then that's typically regarded as something which would readily take up water. And that should probably translate to the type of aerosols which are more soluble as compared to the others. And for aerosols like dust or black carbon, for example, they have like a very low water uptake coefficient, so they don't necessarily deal with water like that.
When you deal with coagulation and stuff like that, is it species dependent? Like every single species has its own like sticking coefficient for coagulation and stuff, or is it modal? Like Itecan accumulates into course or whatever at certain speeds.
Those are modal properties. So like all of the modes are externally mixed with respect to each other. But then within the mode, all of the species are internally mixed. So the composition is uniform across the mode. So the Icon mode would have like, uniform properties across the mode. Same for accumulation, same for course, so on and so forth. This does change in karma. So yeah, like basically you have those exact same calculations happening for each and every bin, as opposed to having those calculations take place for each and every mode. Does that make sense? Yeah. Okay.
I was wondering how improvements in PBL parameterizations have affected the representation of the diurnal cycle of precipitation, especially in the tropics.
So the question is how improvements in the PBL representation have changed precipitation, like representation in the tropics? Yeah. Okay. Well, let's see. So the main innovation in Club in CAM 7 is the introduction of prognostic momentum fluxes. That basically has to do with how the model transports momentum vertically. As far as how it's affected precipitation in CAM, that's a good question. I'd have to look closely at precipitation plots and see like how that's actually affected precipitation. I'm not aware that there are major changes to it. The last thing I was working on was tropical cyclones that high resolution tropical cyclones. So I haven't specifically looked at that, but we could find out though. Thank you for your question.
The previous lecture, they told us about these versions of the model where the nest or the grid kind of changes to a regional finer grid, and they told us that the model was tuned only for the 1 degree version. So my question was, for example, for the convective parameterization, whether the deep convection or does the trigger change depending on the scale? Is it kind of scale aware or something, or is it just exactly the same parameterization regardless of that?
Sure. Yeah. So actually, that project I just mentioned, dealing with tropical cyclones, we did use variable resolution tests, and no, Jean McFarland is going to behave the same way throughout the globe, even if you're looking at a coarser resolution part of the globe or one of the areas that's being refined more. So no, we haven't built scale awareness into ZM yet, as far as I know. But yeah, one of the parameters that we played around with in order to make the tropical cyclones look better was NZM, and yeah, it's a globally effective parameter. Yeah.
So, I started off with Word, where you have all these different options for each of these things. Is that like based on testing a bunch of different the parameterizations and then deciding, or is this all about making sure that it agrees with the physics and keeping it simple, I guess is my question?
You mean as far as like deciding which?
Deciding which pieces to keep from the plethora of options, I guess, is my question.
Yeah, I guess that's kind of a historical question. I mean, I know when Club was being considered for CAM6, there was another model, I think it was called the Unicon, I think, that they kind of did a little bit of a bake-off. And I mean, this was before my time, so I can't go into too much detail about it, but they kind of did a little bake-off, and they sort of decided which one they preferred. I'm sure they took into account things like computational costs and the physical realism of the results and so on. But yeah, I've used WRF, myself, and I know what you mean by all those different parameterization options they have. As far as which ones make it into CAM, yeah, that's kind of a historical process of just model building and decisions that are made over time. I mean, the development process is pretty intensive, and decisions are being made about how to improve the model all the time. And some options do still remain in the code. I mean, like you were saying, you have an option when it comes to aerosol parameterizations. Did you want to say anything more about that? To that question?
Yeah, I can probably add on along the same lines. Yeah, so it's kind of the same sort of a problem with, for example, the aerosols. I guess talking about like a little bit of a history related with, for example, MAM. So MAM4 is the current modal aerosol model, which is in place in CESM or CAM. But before that, we've already had two different variants of MAM. One was called MAM7, which had, I guess, like a completely different treatment of both sea spray aerosols and dust. But then just having those additional modes in the model, that was not very that wasn't very useful for just like bumping up the computational cost of the model. So then we kind of switched around a little bit and then came up with a MAM3 version of MAM, which didn't really have the primary carbon mode, but then not really having a separate or like a completely different treatment of the non-hygroscopic species. That is also like something which was kind of missing out in hindsight. So having a separate mode for that now seems to be the most stable option. And now, kind of working along the same lines, having a completely different option in Karma to represent the aerosols using bins instead of modes altogether. That's like, it's not necessarily the state of the art, but it's something which is currently being researched and developed at the same time. So, yeah.
Maybe I can add one more thing. I just thought maybe I'd mention there is an ongoing effort right now among different modeling centers. It's the acronym is CCPP. I think it's something like Common Community Physics Package or something like that. And it's an effort to sort of overhaul the coding infrastructure of our model and maybe some other models. And I think one of the goals of it is to make the parameterizations more interchangeable, so that if you wanted to switch out, like say Club or ZM or something like that, it would facilitate that and make it a lot easier. So you could test CAM with different parameterizations if you wanted to.
You mentioned CMA as well.
Oh, yeah, there's also a CAM-SEMA effort, which is meant to integrate basically all of NCAR's models, which includes WRF and CAM and impasse, I think, maybe impasse.
Yeah.
Yeah, I think, and yeah, so it's meant to sort of integrate everything, and with CCPP, it would be a very powerful tool because you'd have a lot of options. Yeah.
No, just thinking about Musica, which is the chemistry. I'm sorry. That's the chemistry equivalent of what Ben just mentioned. So like the CAM-SEMA as well as having the MPAS, which is yeah, just the high resolution grid. So the ACOM lab, the Atmospheric Chemistry Observations and Modeling Group at NCAR, they have their own infrastructure, which is called Musica. And I think right now what they're doing is essentially the same thing. They're basically trying to build a model that is capable of handling regional refinement as well as having like a multitude of different parameterization options that are compatible with both CAM as well as CAM-CHEM and so on and so forth. Yeah.
I want to ask you that how if we assess the one physical parameterization such as the cumulus parameterization, we can use the Best-Miller or Jagger-McLean, then the model output will be changed not only by the cumulus parameterization but also by the other factors such as the radiation influenced by the the difference in the cumulus. So how does the modeler approach to tuning that parameterization for making more accurate simulation?
So just to make sure I understood the question, are you talking about like process calibration and model tuning and those types of things? Yeah, so the way we typically do it is by checking if the model is in a proper radiative balance. So like let's say the residual at the top of the atmosphere or the top of the model, for example, that's one of the variables that we like to look at, or the short wave cloud forcing, the long wave cloud forcing, like essentially the radiative flux variables. And we typically assess the model performance of the model simulations using climatological data sets, for example. And if the model seems to be in a good balance, then we call it to be in a good balance. Otherwise, we have different model parameters associated with all of these parameterization schemes that we can, tune a little bit, increase the value a little bit, or decrease the value a little bit, and then see how the model performs as a result of that. So, do you want to add something to that, or?
Maybe not too much to add, but yeah, I mean, like if you bring a new parameterization into the model, which I think is kind of what you're suggesting, like if you did bring in a new parameterization, how would you kind of calibrate it? Yeah, I guess there's not really like a standardized method for doing that. We have different tools that we can use. I mean, one option would be to just go to someone who's like an expert in that parameterization and have them, spend some time working with the model and just trying to tune it. I mean, they understand how it works, and so they kind of know which knobs to turn to make things look a little better this way or that. There are automated tuning methods that you can use. That's another thing that I work on actually, is some sort of simplified automated tuning.
PPEs?
Yeah, and PPEs, perturbed physics ensembles, we also do those here. So those help us to understand the sensitivity of the model output to various parameters. So there's different methods for trying to calibrate like a new parameterization. Mm-hmm.
We can have a final question, if anyone has one. Maybe I'll ask the final question, which is, do either of you, or what are both of your
kind of in terms of parameterization differences between CAM 6 and CAM 7, do you have anything you're excited about?
For me, I mean, the thing that's sort of closest to of like my day-to-day work is Club, and the big innovation that we have coming into Cam 7 and Club, as I mentioned, is prognostic momentum fluxes. So momentum fluxes in Club used to be diagnosed according to like a simple down gradient scheme. That's the way it's kind of always been in CAM, but now we have a full prognostic equation for it that's being turned on, and studying that, I've been able to show and submit a paper by now on how it actually improves the representation of like tropical cyclones, for example, in high resolution settings. So that's pretty cool.
I would probably say Pumas, of course, and like obviously the original microphysics scheme that was there in CAM, that was Morrison Gettleman, like 3 different versions, and then as the team kind of got bigger, we sort of just rebranded the whole thing as Pumas instead. And the one thing which I guess I'm like really excited about having as an option in CAM 7 is the warm rain emulator, which kind of got coupled, I think, a couple of years ago by DJ Gagne. And yeah, like the application was, I think, shown in a paper by Andrew Gettleman. I think it was like 2021 or 2022, basically, comparing with the climatology as well as like in situ data sets. And the performance is quite improved because the emulator itself is sort of based on a bin microphysics scheme. As I was mentioning in the talk itself, that's supposed to be more accurate as compared to your run-of-the-mill like bulk microphysics or moment-based microphysics schemes. So yeah, it basically represents the collision coalescence processes or auto-conversion and accretion in the model a lot better than what we currently have in Pumas. Yeah, that's pretty meaningful to have for us.
Okay, let's thank Ben and Kanishk again. Okay, now we have another break. Come back at 2:15, back to this room.
Hello? Okay, good. Okay, welcome back, everybody. Our next speaker is Cecile Hene. She is going to be talking about, inside the CESM factory, how we build an Earth system model. And she is a scientist and CESM developer in the atmosphere modeling and predictability section.
Good morning, everyone. It's really nice to have this room full of young users. And I'm also the atmospheric working group liaison, and I work really on the atmosphere, but also I do a lot of the coupled mode development. And usually I don't say CSM developer, I say CSM addict, but I saw it will not be good for a tutorial then. Okay, then how long do you think it takes to build a new version of CSM? Then I guess by now you're a little bit familiar with this plot. This is CSM2. Then how long, somebody has a guess? How often do we release new version of CSM?
7 years.
Not far, yeah. It's about 8 years. 7 years is pretty good. And then this is only just one release. Then this is a lot of work. Then what I want to bring you today, it's to explain you why it takes so long and what we are doing. Then the first part, I will talk a little bit about the way we built CSM. Then I will talk about the art of tuning, and then model developmental. Basically, in the first part, I will say how CSM is built, explain what's model tuning, and also why coupling the model always surprises. And by the end of this talk, you will be able to answer all these 3 questions, hopefully. Okay, the first part, building CSM. Then basically, when we build the model, we have different working group. The structure of CSM, it's different working group. And every group develop its own component. And then I like to compare this to a musical band. I'm a musician and I play in a band. Is there any musician here? Okay, do you play in band? But, okay. Yeah, okay. Then if CSM were a band, I say it's like if you had musicians rehearsing separately, and each musician can sound great when they play alone in the bedroom. But then when you couple all the pieces of CSM together, the real challenge really begins. And it's like when you have practiced a lot alone and then you bring all the pieces together, it can be really hard. And in practice, how do we do this? We have weekly coordination meeting across all working group. We have a lot of people of the different part of the model that sit together. We test hundreds of configuration. I'm missing a S there. And then we have thousands and thousands of simulated here. Then it's really a lot, really intense work. And basically, it's why it takes here. And it's an iterative process. We develop, we couple the model, we evaluate, we improve, and then we repeat. And basically, you see the mouse here? Okay. Basically, this is a cycle. And then this cycle repeats for several years before a new version of CSM is released. Then basically, this is how we develop the model. But it's good. People think 7 years. Often people think, oh, it takes 1 year to develop a version. It's much longer than this. And now I'm going to talk about the art of tuning. What's model tuning? Tuning, it's something that's a little bit mysterious usually to people who don't do model development. And when we do tuning, we adjust parameter in the model, what we call the tuning knob. It's like a big button that we can turn to change. And we adjust this parameter to achieve best agreement with observation. Here we have to be a little bit clear. The tuning knob, it's parameters that are weakly constrained by observation. There are a lot of parameters in CSM, and not all parameters are equally well constrained. I never change gravity. This is not something I'm going to change. But you have parameters that are going to be tunable in the cloud microphysics, ice to snow conversion, and I'm going to give you one example of this. And basically, it's this parameter that are not well constrained that we are changing. That to make it really clear, tuning, it's not changing the physics, it's choosing reasonable value for uncertain parameter in the model. And it's how we do the tuning. Then I'm going to present you one of our tuning knob. It's not something that we use a lot these days, but we have used it a lot in the past, and I think it's really clear. Then it's a parameter called DCS. It's a parameter that controls when a cloud ice in the model becomes snow. And to illustrate what it is, you have here on the picture, you have the Flatiron, the beautiful mountain there, and you see this really thin cirrus cloud, white cloud on the picture. They are composed of ice crystal. It's what we call the cloud ice, and typically they are above 5 kilometers. And then when the ice crystal is going to grow, at some point they're going to grow, and when they're big enough, they're going to fall. This is like the little orange dot. This is the ice crystal that fall out of my cloud. And basically, DCS is the size at which the ice crystal began to fall as snow. And typically, this is like between 200 and 600 microns. Then it's a parameter you can change in the model. And if you look in reality, you have ice crystal in the cloud. They are not going to be all the same size. Right now in CSM, when we change this, they're all the same size. Then it's an approximation. Then it's why it's a parameter that's very weakly constrained, and you can tune it. But I'm not going to do ice crystal data, for example, 1 meter. I know this is not happening then. And then what happens if we change DCS? And here I have built 2 clouds. On the one side, I have here a cloud with smaller value of DCS. Then I have less cloud ice because all this big crystal has fallen out of my model. And here I have a larger DCS where I have more cloud ice. Then what do you think is going to be the impact on the climate? Which side do you think is warmer? Any clue? I'm going to give you a little hint, then think about the infrared radiation. Then do you think it would be easier for the infrared to go through the cloud with less cloud ice? Or this one? Yeah, then this one, the one on this side, it would be easier. There is less cloud out. Then you will have more infrared that's going to escape, and you will have a cooler climate. While here you will have the opposite. And how does DCS is going to change the Earth energy budget? I'm sure you have seen this kind of picture. This is the Earth energy budget with the incoming solar radiation, what's reflected by the cloud, what's reflected by the surface, the outgoing long-wave radiation. There's a lot of things for the radiation budget. Then where is DCS going in this picture? Any clue?
Maybe here, yeah, change of the infrared. It's going also to be
have impact on other, but mainly this is here where we are going to put the DCS because it's going to impact the infrared radiation. And basically how this is going to work globally for DCS, this tiny parameter, you modify DCS, it's going to modify the amount of cloud ice you have in your model. Then the infrared radiation is going to change, and then it's going to change the Earth energy balance, and you will change the global climate. Then this is really the processes that you have here. But then why do we even care about having the Earth energy balance close to 0 in CSM, especially when you do a pre-industrial simulation like the one you started in the morning? We always try to adjust to have the energy balance that's really close to 0, like within 0.1 watt per meter square of balance. EIF, it's a real simulation that we had done, and in this simulation, I was not close to 0, I was closer to between 2 and 1 watt. It was going down. What do you think happens when we have this? If I inject, I have my balance at the top of the model that's off. Where is this heat is going to go? Can it go warming the atmosphere? The ocean, yeah, because the atmosphere has a very small capacity, then it's going to warm the ocean. And basically, this is what I see when I did the simulation. You see that the temperature of the ocean is slowly increasing. Then even a small energy imbalance causes the ocean to warm slowly. And usually when I have a simulation like this, it takes like a few days until I have the oceanographer coming in my office and saying, this is not okay, you need to adjust this. Then this is what we can do with the tuning. And then also, tuning, there is not like a single best solution. Then here I'm talking about the Earth's energy balance, but it's not the only target that we do when we tune. We try to match observation of the cloud, of precipitation, of ENSO, of the AMOC, of the sea ice, and we are looking at a lot of parameters. And often what happens, the challenge is that when you improve one aspect of the climate, it often makes another aspect worse. Then it's really a lot of compromise. But I think the take-home message of this section, of the tuning section, that it's rarely a single set of parameters that optimize every aspect of the climate system. Then you have really to always to decide which parameter you are going to do. And I want also to say tuning is a balancing act. It's not an optimization problem. You are adjusting to try to reproduce observation. And what's interesting when you tune is that you're also learning a lot about the model. When you are doing all this experiment and then the picture that I was showing you, then you are really learning a lot about the model when you are doing this. Then now the last part that I want to talk about, it's I'm going to show you what I call model developmental or little story. And I'm going to take you, I have been doing CSM for 20 years, then I have a lot of stories sometimes that are older, but I found they are really relevant. Then why does coupling change everything? And here I'm showing you an example. If I do an atmosphere-only simulation, and I work a lot with the atmosphere, I do this often, you prescribe the sea surface temperature. Then you give observation to the model. And when you do this, even if your Earth energy balance is off, the model cannot, nothing is going to happen because you always tell it the surface temperature is this. Then you cannot warm up the ocean, it's prescribed. Then you have a really well BF model when you do this. Once you do the fully coupled simulation, you put under the atmosphere a full active ocean, you start to have coupled bias, you have feedback, and you can have very quickly a runaway unstable simulation. And it's something that we are dealing a lot with. And I always say coupling is unleashing the beast. And then you put everything together, and then there are a lot of issues. Then the first story that I want to explain here, it's, I like to call this simulation the perfect simulation that was not. Then it was during the previous version, it was CSM1, it was in 2009, and we had done a lot of simulation in the atmosphere, and we had a simulation that looks absolutely perfect in terms of the shortwave cloud forcing. We were so proud, we had changed parameterization, it was really, really good, and we were really, really excited. And then we put this in the model, and even this perfect simulation, within like 12 years, it's completely unstable. You see this big bias that I have here in the North Pacific. You have like huge sea surface temperature error. And you see that this is the evolution year to year, year one. Then it goes really quickly. Already after 1 year, it starts to cool. Then we were really disappointed, and then we started to try to understand why the Pacific, the North Pacific, was cooling that much. And basically, we were starting, the SST were a little bit colder. We had, the cloud forcing looked good, but then we were ending up with sea surface temperature that was a little bit colder. And because of this, I was getting more cloud in the North Pacific. And when I was getting more cloud in the North Pacific, my SST was getting even colder. And then it was a feedback. And then with this colder SST, then the sea ice was starting to grow in the North Pacific here, and then when the sea ice grew, it was even getting colder, and it was a runaway simulation. Then what we had to do at this time, we had to do the shortwave cloud forcing a little bit less perfect, and then to avoid to have this effect of runaway simulation. And yeah, it was this unleashing the beast. And then what it really points us is that success in atmospheric only simulation doesn't guarantee success in coupled simulation. And it was really a lesson that I want you to keep in mind, and it's true also for other component. Then second story, then it was when changing the dynamical core, change the climate. And this is another version. It was CSM also 1. It was in 2013, 1.2. And we wanted to change the dynamical core from finite volume to spectral element. In CSM3 now we are using spectral element, but in CSM1 we had already version of the spectral element dicore. And again, I did a lot of atmospheric only simulation, and we had basically identical climate. It was even boring. It was looking the same, like indistinguishable. And then when I put a couple, then suddenly the simulation, the spectral element simulation ended up half a degree colder than the finite volume. And this was a showstopper. We could not use the spectral element dicore because of this error. Then why did the coupling create such a big difference? And I'm going to explain the mechanism in the next slide. But it's again, this is like standalone simulation, atmospheric only, it looks beautiful. You go couple, and then it doesn't guarantee at all that your couple simulation will work. And I'm going to go quickly over this process, but what was happening while the climate was becoming colder? It was, I have a picture here of the zonal surface stress. And this is the oceanographer. They always put the south on this side of the plot in the atmosphere with the opposite. Then if you are, this is the Southern Ocean. And you see that this maximum here move north from the black to the red, just a little bit north. It's really tiny. I would not, if you imagine it was doing anything. And then after we realized it was the whole source. We looked, there were a lot of small differences and we could not determine, but this was what creating the problem. Then what was happening is that we were very close in region of upwelling, and then we had upwelling of cold water anomaly. And then after this was carried over by the ocean circulation, and it's why we had this drop in temperature in the spectral element. Then basically this was this small, tiny atmospheric change that propagates through the couple system, and it caused the global climate. And then my last story, then this is the Labrador Sea mystery. And this is, again, it's hitting us right now. It was a problem in CSM2. But we were developing CSM2, and everything looked like promising. It looks really beautiful. It looks good until the Labrador Sea freeze. And then this is, for people who are not familiar with the Labrador Sea, I show here, it's the sea ice extent. I show you where you have, I'm looking at the planet from the top, and this is the Arctic, and you see here the sea ice extent. It's where you have sea ice in the model. And if you look here, you have a very thin black line, is the observation. And then you see that the sea ice extent in CSM1 was very close to observation, and the Labrador Sea, which is this thing over here, was ice-free. In CSM2, it was what was happening. The Labrador Sea that's here was ice cover. And this was a showstopper, and it gave us almost, over a year, 1 year delay, this issue. Then why was the Labrador Sea was freezing? And it's because if you look in CSM1, the Labrador Sea is here. It was too warm. It's the SST bias here. And I was too warm and too salty in this region. But in CSM2, I was too cold and too fresh. Then the errors are opposite. But in this case, in CSM1, it was helping my Labrador Sea not to freeze, while here, even it was an error, it was not correct, but it was helping me with the Labrador Sea not to freeze, while here it was freezing the Labrador Sea. With this water south of Greenland that was too cold and too fresh, it was freezing. And then it was a problem that was incredibly difficult to fix. We had this beautiful CSM boat that was stuck in the Labrador Sea. And then I always say, this is Dave Lawrence. At the time it was Gökhan, the chief scientist, and it's all the people, developer, pulling the boat here. But it was really robust. We will start simulation, and then we solve it, and then it will freeze again. And then how this was solved, at some point, the oceanographer that was working on completely something different, they were working on an estuary box model. Don't ask me what it is. You ask an oceanographer, but it's some people who know. But they were working on this parameterization, and indeed, it corrected the freshwater transport problem that we had here. If you look here, the surface salinity it became more salty, and it became warmer. And because of this reduced salinity and the SST bias, then the Labrador Sea was no longer freezing, and we had simulation that was stable, and we were able to release CSM2. And right now in CSM3, we have again problem with the Labrador Sea that can freeze again, and it has been slowing us down. And then I hope I have convincing you that coupling is unleashing the beast. Then what did we learn today? I told you we had 3 questions at the beginning of the talk. Then the first one is how CSM is built. And we saw that building a new version of CSM takes many years. We have repeating cycle of development, coupling, testing, we improve, we repeat. And it's a very long process. We talk about also tuning, and tuning basically choosing scientifically reasonable value for uncertain parameter to improve the simulation and to make it closer to observation. There's nothing really like magic about this. And then why coupling is challenging? Then you have interaction between the atmosphere, ocean, land, and sea ice that can create behavior that don't appear on the standalone simulation. And it was exactly what I showed you in the 2 first examples. And usually understanding this interaction, it requires really detective work. It's super fun to do. It can be extremely frustrating because sometimes you understand what's wrong, but you don't know how to fix it. But this is why it's so slow to build a model. Then my last take-home message is that the CSM factory doesn't produce a model in a single pass. It's not like building model, put them together, and give them to the CSM tutorial. Every release is built through years of development, testing, surprise, and scientific detective work. Okay, thank you. And I want to put this, then this is really funny because everybody does like cartoon with ChatGPT. I use a lot ChatGPT. But in this presentation, all the cartoons are done by my son. This one is my son that in Minecraft, the building. My son is almost 25, but he did this in Minecraft. And my husband did all the little cartoon. And that's why I asked him, can you draw like somebody with sea ice and a planet? And he's a space physicist, but he likes to draw. And it's the non-artificial intelligence of my talk. Okay, if you have questions, otherwise I would be around all week. And yeah.
Do we need microphone?
No, they're
okay.
on.
Yeah.
Oh, I'm curious when you do the parameter tuning, if you're like evaluating the impact of all parameters all at once, or if it's like one at a time. Because I'm wondering if like, okay, if you think about like energy balance, could you overtune one and then that, I don't know, solves.
Then this is a very good question. And for a very long time, we are doing often one parameter at a time.
Because we had model that we try to do automatic tuning that we will test. We will have value of several parameters, and then you find where you have the best representation. And for a long time, all these models were not beating the expert. Then it was very hard to tell to a model how to do this optimization of the parameter. For CSM3, we have right now, there are some tuning that has been done by QuadTune. Ben Steven, that was in the talk just before me, has been really involved into this. and somebody from the University of Wisconsin, Vince Larson, and they're doing this, and now we have set of parameters that are tuned with the quad-tune, even that we are redoing some adjustment a little bit manually. But with the quad-tune, they do several parameters at the time. But when we do the problem, when you change one thing, you see you can have all this feedback, and then sometimes we change two things at the same time, and then after we cannot understand it, we have always to distinguish. Then we tend, when we do it manually, to change one parameter at a time and try to understand what's going on. And we don't have there are tons of parameters in the model, but we use a few tuning nodes. It's less than, for the atmosphere, it's less than 10. It's not like we have hundreds of parameters that we turn in all direction. We are trying to adjust. We see that we have this energy imbalance. Usually we will act on the cloud, like I was showing in this example. It's not the one DCS that we are using anymore, but this one is more easy to understand, that the club parameters that are a little bit hard to figure out. But this is really the kind of, we are going to adjust slightly the parameter. And what's interesting, it's tuning the model doesn't, you can tune it two different ways. There is not and have more or less the same result. And it doesn't really impact very much the performance of the model. And if you tune a little bit differently, the model behave more or less the same. but you need to adjust things not to have a running away simulation.
Now that you mentioned that you...
Yeah.
It's okay.
Yeah, go ahead.
Okay, sorry. So you already mentioned you have made 10 main parameters that you can tune. What variable, which parameter you think is the one that shows higher sensitivity, or the model? For which parameter the model results in higher sensitivity? What do you consider the most important tuning parameter?
Usually we have parameters that adjust. We try to change something that we really look at a lot. It's the energy imbalance, and it's in the last step in the model when we do this small increment. And then we change a little bit the cloud. And then by changing the cloud, you are going to adjust the model. But we look also, there are some parameters that affect the precipitation. You can have evaporation coefficient that are important too. And we do this as a team usually to see which parameter we are going to play with. Somebody there is Ben that was really involved in the tuning this time, and then there is also Adam Harrington that will give a talk on Friday, and he is also really involved into the set of parameters. Then, yeah.
I was just curious about if you could comment on some biases that came up during CESM3's development, and if there are any biases that we should be expecting when it releases, and also if it's doing better, because I think you've used MOM for Ocean, so if the whole CIS parameterization is better now from CSM2.
Yeah, right. The issue we have again in CSM, we are almost done, but there are two aspects that we are still struggling a little bit. Then there will be, we have instance of the CI is freezing, and we are trying to solve this. But then in other version that we will not have the CI is freezing, we have the ACC of MOM that has too much oscillation, and this I'm not an oceanographer, then I cannot explain the detail, but they're very concerned about this. Then we have, this is where we are very concerned. But we hope it will be released in the first few months. And I mean, I have been using CSM3 for several years already. Then it's a good model, but you are a little bit in this transition period that we were thinking, do we teach them CSM2? But in a few months, we will have a new model, hopefully. And then we prefer to teach you CSM3. One of the issues with CSM3 is that it's more expensive than CSM2. Yeah, that's perfect. But otherwise we can, yeah, I'm available all week.
Yes. Cecile will be in most of the sessions helping out as a helper. So continue discussions in those sessions. Thank you.
Okay.
That was our last lecture of the day. But now we're going to return back. Oh yeah, thank you.
Don't go to the bathroom.
We're going to return back, not yet to the lab sessions. Before we do that, I have a check-in slide deck to show. Yeah. Yeah, so we'll go just for 10 minutes, we'll run through these slides. It's kind of just to make sure everyone is more or less on the same page with the resources. And then we'll go back for our second PM lab session. And then after that, I'll announce it. We come back in here for a short wrap up, do the survey, and then we disperse for the day. Okay, so the first kind of thing I just want to check with everyone is that they're aware of the CESM tutorial website. So this is separate from the materials you've been dealing with. Here's the link to it up there, or you could just search CESM tutorial 2026 NCAR. It's got logistics, photos, the agenda, and in that agenda is where you're going to find the links to all the presentations. The lab materials are also linked right there. And then also, I hope that you all found the lab documentation. Here's the link to that. And just for your basic expectations of how the days will go, we'll have a lab every single day. So today you've been doing the basics lab. On day 2, it'll be the simple XML modifications lab. Day 3, we'll have a nameless troubleshooting and source mods lab. Day 4, and everyone does day 1 through 3 together, the same exercises. Day 4 will be, actually these should be switched, and that's my fault. Day 4 will be diagnostics. And so that's where, we're gonna get into the specific plotting of maybe components you might be more interested in. And so you can kind of choose your own path on that day. And then on day 5 will be the challenge exercises. And so, every different kind of specialization has their own challenge exercise, and you can choose maybe 1 to 2 to do that day. But all that said, this is the general layout, but this is very much a self-paced lab. So it's completely fine if you're still doing basics tomorrow, or if you want to skip ahead a little bit. Either one is fine, and we all come from different backgrounds, so we're going to have different learning rates and different ways of doing these labs, and so that's completely okay, and it's okay to ask questions about a lab that's on a different day than what we're doing. So also want to make sure that everyone is aware of doing the prerequisites for success and tutorial one-time setup sections. These are the kind of critical sections that teach you about, what do you need to have downloaded on your local machine to get X11 forwarding, or what do you need to do to set up you're using the right project and the right queue when you run your simulation. So make sure you are checking out and reviewing these 2 sections. Also, just so everyone is aware, as a full-time participant, you should have access to this account number, and you can use this for all of the tutorial exercises. The reservation queue is tutorial, and so it's really critical to use that queue, because if you don't set this queue, you'll be using the main queue, which is basically everyone's queue, and so it's going to take a lot longer for your runs to, you're going to be waiting in the queue for much longer. And just so you know, you can use this tutorial queue all week, but it'll end on Friday. And if you submit with the tutorial queue, I think past 5 p.m., it will automatically reroute to the main queue. So it's only active during the daytime, but you can use it. You can use the queue. And then, I'm sorry, auditors will not have access to these this account number and reservation queue. If you're curious about how to make sure you're setting the tutorial queue in your case, XML change job queue equals tutorial -- force is how you make sure you're using that tutorial queue for your runs. And then I got maybe a couple comments on this, which is just to clarify that in the basic section that you've been running through today, there's an initial part that is the CESM workflow, where it's kind of telling you about what the commands are, but not expecting you to actually run them. So, don't be, if you enter a command when you're in that section, you might get some unexpected results. And so this is more so informational to show you the CESM workflow. You don't start to actually run the commands until you get to the exercise overview. So it's really when you click on those green boxes and you see the solution where you're in the right place and you should be, running those commands. I think that's it for my slide deck here. Yeah. So do we have any questions?
Okay, everybody
all up to date? Everybody's got everything under control? Great. If not, it's totally fine. We're gonna start the PM part of the lab session. And so now we're all gonna walk up to the library.